the cameras. We did that so that no more than 7 people are up here at one time. So if you do want to have multiple people, that is completely fine. I would just have you guys kind of standing on the side and rotate in, if that's possible for you guys. Because I know some of the teams are larger, so we didn't have the capacity to fit 40 people up here at one time. So just kind of, you have some time right now, a little bit of time with your larger teams if y'all want to talk amongst yourselves and decide how y'all are going to rotate in and out. But okay, if you think of anything, just come grab me. I'm going to go chat with this team in the back here. This is not mine. Okay. But I did notice some of them are quite long. Please keep in mind you have like 7 minutes exactly. Okay, so if you have 35 slides, do the math on that. You got to whiz through those really quick. So just be cognizant of the time. I will do my best to kind of stand in the back maybe and cue you guys with like a, hey, you got 2 minutes, because we want to give the panel time to ask you guys the questions. Okay, so don't talk too fast to where you're, losing sight of, the meaning of your PowerPoint, but really, your PowerPoint better than anybody else. Focus on the slides that matter the most, okay? But 7 minutes, plan for 7 minutes to present. Another thing to note too, the priority today is presenting to your exit panel. So obviously you want to be aware and, kind of look at the camera from time to time, but your main focus is going to be these lovely individuals over here is that's your target audience here. The people that are logging in online are interested in hearing what you have to say, but they have no say in what you're doing today. And this is where your questions are going to be coming from. So just keep that in mind. Just know, blocking as far as body goes, you're going to talk to them, maybe turn back here, Yes. The link is in the Discord. Yeah.
Our program will begin momentarily. For your safety, please remain seated at all times during the event. In the event of an emergency, exit the ballroom through the exit doors on your left, turn left down the driveway, and walk to the grassy area to the west of the parking lots. Do not stop in the drive or parking areas. This will hamper emergency vehicles responding to the emergency. As a courtesy to our speakers, please turn your pagers and cell phones to their off or vibrate position. Thank you for your cooperation.
All right, so now would be a great time to silence your cell phones. That would be very helpful. If you have alarms that normally go off at this time, also double check those so that we are not having lots of alarms going off at the same time. Thank you guys so much. All right, guys, you did it. Welcome to the 2024 NASA Suits exit pitches. You've made it to the finish line. We are so proud of you guys for all the hard work that you have put in this week and beyond. All the months of hard work really paid off, especially yesterday, seeing everything come together. So well done. Quick round of applause for you guys there. We are honored to have our exit panel here with us today, and they are going to take a couple minutes to introduce themselves to you guys so that you know who you're talking to and who you're pitching to today.
Hi, everyone. My name is Paramita Mitra. I think I've met a lot of the professors in the room. Today, my role at NASA, I'm on the Lunar Architecture team as the Data Systems Sub-Architecture Lead. So, but previously, I have worked with Suits. In the beginning of Suits, a lot of my graduate research helped inform kind of how we structure the challenge, and previously also led the Joint AR project where we built a heads-up display for the XEMU Suits. And so it's really exciting to see you all here. I am so excited to hear everyone's exit pitches this year and see how test week went. And so, yeah, good luck, everyone.
Good morning. Welcome to Johnson Space Center. I hope you've had a good week so far. I'm Cindy MacArthur, and I'm the Deputy Director of the External Relations Office here at JSC. It's the office which OSTEM, Office of STEM Engagement, sits in. But my background really has been in education for most of my NASA career. I was the Director of the Office of STEM Engagement here and had the pleasure of watching Suits in the beginning and then reach this maturity where we just love having students here on site. I also served as the External Relations Office representative supporting the International Space Station program and commercial crew, and I'm thrilled to be part of the panel and look forward to your presentations.
Hi everyone, my name is Katie Tour. I'm a computer engineer in the simulation and graphics branch here. I work on the prototype immersive technology team. So some of the work that I do here is related to what you're giving us presentations on today. So I'm really excited to hear your experiences throughout this whole project. I work on lunar surface, EVA, virtual reality technology, and also lunar lander simulation technology. Some of the other things we do in our branch is related to creating simulation technology related to training and analysis. So I'm really excited to hear all of your experiences today, and thank you for all of your hard work.
Testing, okay. My name is Tim Hall. I'm the Strategic Communications Manager for EHP. So what's that mean? Well, EHP, hopefully you guys know by this week, is the Suits and Rovers program here at JSC. And StratCom Manager does things like everything from public affairs to internal comm to the programs. But my career has been a kind of chaotic and sometimes a collision of communications and engineering, because I have a mechanical engineering degree from schooling. I spent about 20 plus years in mission operations here, flight operations they call it now, in JSC. So at one point I was the branch chief for the team that trains the astronauts how to do spacewalks and supports them in real time in the MCC. So I have suits that are very near and dear to my heart. So I can't wait to see your guys' presentations today. And I love this is where the rubber meets the road when you guys go out and try to actually implement what you've built and see how operations affects that. I'll give you one other tip. Hopefully got a second. I can't express how important this is to your guys' careers, and that is just presenting yourself. Because as engineers, you tend to be introverted, and you will have challenges doing this. Some of you I've heard of, would rather parachute out of a perfectly good airplane and be in front of an audience like this. Please, any chance you get, challenge yourself with communicating and putting yourself on the spot in front of people, because it will help your career. Believe it or not, the only way I got to do it, you ever wonder what happened to Jungle Cruise skippers later in life? I was a Jungle Cruise skipper at Disney World for a couple of summers. And that brought me out of my shell, and it's tremendously helped me be a better manager, better mechanical engineer, better team member. So please push those communication skills as much as you can, because it's going to be important to your career. So, and can't wait to see you guys today, how well you do today. Thank you.
All right, thank you guys so much. I'm excited to hear all the questions that you guys are going to ask our students today. Are y'all ready to get started? Yeah? All right. Are we ready in the back to go ahead and get started? Wonderful. We are live with the 2024 NASA Suits exit pitches. We are going to start today with Team Claus from the University of Michigan.
Hello everyone, we are Team Claus representing the University of Michigan. We're a project team of 70 plus members participating in the NASA Suits Challenge. Can I get the clicker? Thank you. Today we'll be presenting our application, IRIS, which is the Immersive Reality Interplanetary System. So our application IRIS has two different interaction modes. The primary one is voice commands, because astronauts often have a multitude of things to do with their hands, so we wanted to ensure that they could do things within the application while still being busy. Additionally, we have touch input as a fallback in the case that microphone or the astronaut is unable to talk at that point. For touch inputs, we also allow for hand raise and large buttons to ensure that the UI is easy to use. Additionally, a large part of our application this year is the inclusion of modes. We noticed in our user research that when astronauts were using our application, there was different requirements that they had for different tasks. So for example, within geosampling, they'd be within one zone for a long period of time. We wanted to update our UI to reflect these changes, and what this led to was the creation of modes. So for example, in geosampling mode, the screens will be attached in space rather than to the user, and in navigation mode, the screens will be to the side to ensure that the astronaut is still able to easily navigate.
Yeah, so this is kind of our main menu. We tried to have an interface that would be very open and not overwhelm the user, but show vital information as it kind of appeared. You can see there's a notification in the top left, which allows the astronaut to see like message alerts, vital warnings, DC recommendations, as well as when like a new task or waypoint is created. There's a mini map that shows waypoints that aligns with what the astronaut sees in their field of view. And then in the bottom, there is a small task window that shows the astronaut's current tasks and allows them to expand for more details, as well as check off the box to complete that subtask. So geosampling mode kind of represents how modes are laid out across the interface. So you can see here different geosamples appear around the user's display. The mini-map zooms in, and then there's a persistent notification at the top that shows information about the number of geosamples scanned in the session, as well as the number starred by LMCC. And there's also a toolbar at the bottom that provides different buttons relevant to the mode, as like add sample and to view the samples created.
Next, we could talk about geosampling within LMCC. Every single feature has its own LMCC counterpart that allows for communications between the two. Our idea with LMCC was that we wanted us to be able to do anything in LMCC that the astronaut would be able to do in the HoloLens, just to ensure that there was less cognitive load on the astronauts. Within geosampling, we allow for the ability to star samples of interest, and LMCC is also able to automatically star these samples. Here you can see what a star geosample looks like in AR. We changed the color of the waypoint to gold.
For the geosamples on the AR side, you can select to create a sample in a specific zone, and this is directly reflected on the LMCC side, and the LMCC operator can edit any details that will also be reflected on the AR side. For the for the database, you can basically see all of the different geosamples within each zone and see any vital information as well. The navigation, you can select the navigation on the main menu and then navigate to any waypoint you want. When you start navigation, a confirmation screen comes up which shows how far the waypoints are and also how much oxygen consumption that will take. The navigation on the LMCC side has a map that shows all waypoints. The LMCC operator can also create, delete, or edit any waypoints for the AR to see real time. And then the LMCC also has a map that is updated real time that shows all waypoints, the rover, all the astronauts, and on the left-hand side, a live feed of the astronaut. The 3D map can be spawned in front of the user, which is an interactive map of the entire terrain. You can see all waypoints, all pathfinding information, and you can zoom in and out and start pathfinding as well.
We also allow for messaging to allow for the LMCC to message astronauts, and astronauts allow them to message each other. This is a good redundancy as well for voice communications. Sometimes they go down, we have messaging. And this also allows for the LMCC to send mission details to astronauts. For task list, this allows the LMCC to send task details and mission details through a task list system. It allows astronauts to mark tasks as in progress or the LMCC to mark them as emergency tasks to prioritize them. We also have vitals. It allows the LMCC and astronauts to keep track of their vitals effectively, and we also send alerts and notifications to them to allow them to respond effectively. Lastly, we have an AR web connection system to send images and highlight menu buttons to reduce cognitive load for astronauts and put some pressure on the LMCC itself.
So our application includes hard-coded voice commands using Unity, and these are listed in the bottom right of the field of view. These commands are context dependent, so depending on the mode or screen you're on, they'll change. We also pass certain commands through a more complex language model, which allows us to comprehend complex commands. For example, multi-step commands can be broken down and condensed into one command, which will be processed by our model, and allows procedures which would take multiple voice commands to be condensed and reduce the time it takes. For our computer vision functionality, we have a UIA panel tracker, which allows us to place UI components on the UIA panel, which reduces the cognitive burden of identifying which inputs to use, and also reduces the risk of using the wrong inputs. We did this using a custom lab color space identifier, which helps us track colored markers on the four corners of the UI panel. So when it comes to geosampling, it's important for an astronaut to survey a large amount of area for potential geosamples. So we created an automatic geosample detection system, which allows us to identify geosamples and place a basic description on a label in AR on the actual sample. So we did this using a YOLO V8 pre-trained regional proposal network, in addition to some basic CV techniques to create the label.
Now we can get into the hardware components of IRIS. The first of which is the Cardiac Orientation Reporter, which is CORE. Core is essentially a hardware IMU that we attach to the user's chest to get the heading data of where they're facing. This essentially allows us to increase the FOV of the HoloLens because we saw in user interviews that the FOV was one of the major issues when using the application. Basically what happens is the screens are attached to the body rather than the head, and that allows you to move your head around while staring at the UI. We also quickly made a hardware visor, which acts as a way to use the HoloLens in highlight conditions. We did this by cutting out some car tint.
So our third hardware component, which we look to complete in the future, is called Scout. It's a 3D mapping rover. We wanted to think about how a program like Iris could be used to facilitate coordination and cooperation between an astronaut and an autonomous robot aid. In this case, Scout is a navigation assistant, which would create a 3D map of the terrain using a 2D LiDAR for localization and a 3D depth camera for the point cloud. It could create a 3D map that could send and display for the astronaut to assist in navigation and make sure they get to their destination safely.
We held a number of educational outreach events to share the exciting AR technology with the next generation of students. The Middle School Hour of Code and Aerospace Day helps students from K to 12th grade utilize their own mini AR interfaces and learn the basics of block programming. And finally, we talked to some high school students visiting our college campus and shared the mission of CLAWS.
We have also designed a study in which we will evaluate user responses to different interface icon colors and text sizes on the HoloLens under varying red lighting conditions. This information can then be used to present informed design decisions and better understand task performance in a Martian environment.
So that was our application, Iris. We thank all of you very much for the opportunity to present today. And panelists, thank you very much for listening. We're open to any questions.
Just out of curiosity, it looked like you're collecting a lot of biomed data for the crew member, right? Is there anything, one thing in EVAs today is we really have to watch on the ground consumables we're using, and then we relay to the crew members how much time they've got left in EVA based on that. When you're on a Mars surface or a lunar surface, you want to have that more immediate to it. Do you have a way the crew member that you do some kind of calculation to estimate what's the lowest consumable and tell the crew member that that's what you need to track? Either O2 or CO2 scrubbing? Anything thought through on that?
Yeah, I can talk about that. So I will say that's one of the things we were looking at a lot during our application. So you could see during the navigation screen, they actually showed the amount of oxygen that would be taken up, the amount of battery pressure. But we also include elements that make sure that both LMCC and the astronaut are aware of their vital situation. So for example, if one vital goes too low, like off a nominal range, then we'll immediately notify both the astronaut and LMCC, and they'll be able to take the proper steps to fix that. So the general idea is we try to make the application do as much of that to offload a lot of that stress from the LMCC operator and the astronaut.
And just to add a little bit more, we're also really focused on not overwhelming the astronaut because we know it can be a little bit intimidating to constantly see all the numbers changing and flicking back and forth. So we hid that behind one menu. So you can say open vitals or just press on vitals and see all 20 or so vitals. And then if anything does go wrong and something drops out of range, the astronaut will immediately get a notification. And then LMCC is constantly monitoring at all times the vitals and also gets the notifications. So we're kind of trying to balance providing the astronaut with information with kind of managing cognitive overload.
That's good thinking. Good job.
Hey, great job, Claus. I had a question, maybe two if I have time, but the first is for the IMU mounting location. They're very specific to how you mount them. How were they mounted? And did you experience any drift issues or anything?
Yeah, I can talk about that. So for the IMU, we did mount it on the chest using kind of a belt. I think that is one of the things that in the future we want to do a little bit more research into, because there's a lot of accidental movements that happen when you're looking at different screens, and we want to make sure that head movement is not being tracked and body movement is being tracked. So that's one thing we want to do research on. In terms of drift, we definitely did experience drift. I think that's an issue with a lot of IMUs, and we also didn't have the most expensive IMU. But in order to counteract that issue, we had functionality like what we called core sync, and that would essentially put the screens right in front of you. So if there was any drifting or some kind of like network interference, we would allow for that correction to happen.
Thank you. And my second question is, you have a team of 70 people. Is that what? Did I hear that correctly? That's amazing. What are some of the pros and cons of having a large team?
Yeah, definitely. I could talk a lot about that, but for pros, I'd say immediately we have 70 people, so that means there's a lot of parallel work that can go on. Within our club, we had like a setup where we had different phases, and in each phase we had about like 8 features going at a time. So this meant that 8 different components were being developed in parallel across these 70 members. So just like because of our large team, we were able to have an extremely large scope when we were creating our project. I just say in terms of the cons, the one thing is that it's pretty difficult to coordinate everything, and when you have a team that large, there's a much larger focus on making sure everyone knows what they have to do, what the requirements are, what the expectations are, and just making that very clear to the members was very important for us.
Thank you.
Hi, thanks guys. This is a great presentation. One of my questions I had was about feedback like after your design session. So did you get any, like, do you have any feedback based on like the extension of your headset to get the wider field of view? I thought that was an interesting like idea, like a great idea to add.
I'll say for the extension, I'll say people did enjoy the ability to really just like have screens be where they want them to be. So I think one of the issues we dealt with last year was the screens were locked to the head, and that kind of made it so that if an astronaut was doing a task and the screen was in the way, they'd have to like move their head out of the way and like look with the left of their eye. And I guess what we kind of figured out was the second people are changing their behaviors to fit the application, we know something's wrong. So what we realized was fixed this year was if someone wanted to have their screen here, we could say core fix, and then it would leave the screen there. They would be able to do whatever task they wanted. They could reference it if they wanted, and then they could say core follow to bring it back to them. And then they also have the ability to see more things on the FOV because of that increased FOV we were talking about.
Well, thanks. I think you answered a question that I had about personalization, because I think we're so accustomed to that. But I was just curious, what was the hardest part of all this adventure to get you here? What was the biggest challenge?
Yeah, I can definitely say what I believe the hardest part was for me, but I think it also depends on what everyone was working on. As the project manager, I believe the hardest part for me was really taking the time to establish what our goals were, what our requirements were on a daily basis, really just thinking about what expectations we had for every member and what we wanted to be done by the end of each phase. I think that was a difficult process, especially with 70 members, but I think it was also a very rewarding process. I think other members of our team are willing to share the difficult things that they had to deal with in the process as well.
I guess to be quick, I guess for the AI side, we had a lot of heavyweight models we were using during testing, so you can't really bring that on site because we don't have internet connection. So I think that was a field where we had to make a lot of sacrifices with our interface.
I could speak for the LMCC. A lot of the times we didn't realize that the connection between AR and the LMCC itself was a big connection. And a lot of times we needed to make sure that the data we sent between each other was really important, and we actually put that off towards the end. We ran into some trouble with that, but it did end up working.
For the AR side, I would definitely say the connection with LMCC was a difficult part because, again, the Wi-Fi and all of the connection issues that can go on with the HoloLens and so on. I think the main thing was also the voice commands that we had trouble with, and we had a lot of fallbacks, which we planned for because of the past few years of all the research we've done. So everything planned out pretty much perfectly with all the fallbacks. So, yeah.
Thank you, everyone.
Thank you, Team Claus. That was wonderful. I cannot imagine coordinating with that many people, so well done. Next up, we have Team Daedalus from Rice University and Georgia Tech University. Come on up.
So hi, everyone. I'm Melissa. This is Michelle. We're representing our team that is both Rice and Georgia Tech. We're a bit of a smaller team, so we have about 9 people total. Most of us are either computer science, engineering, or human factors, and we're both graduate and undergraduate students. And so we approached it through more of a human factors, what are we trying to solve? And then from there, what questions do we need to ask to be able to build our system? And so our main objective was to build an AR and an LMCC system where the primary goal to be a tool so that it can aid the crew in executing their missions while they're doing an EVA. That is very broad, so we tried to narrow that down into what are the 3 main goals that we had. The first is that we wanted to streamline menial tasks. The second is we wanted to use the headset as a memory aid so that cognitive load can be lowered in an astronaut. And we wanted to reduce overall human errors that could be avoided if there's redundancies within the system. The way we did that is first for streamlining menial tasks, instead of individuals having to navigate and drop their own pins to follow back home, we created a breadcrumb feature that allows the astronaut to just click a button, and as they start walking, every 2 meters, a breadcrumb would fall, and then they could just follow that line back home. We also wanted everything to function as a memory aid, so you didn't have to remember pages and pages of documentation and what to do. So the egress procedure is very complex, a lot of steps, and so we created a system where all the instructions are presented one at a time so that you can focus on the current task you're doing and then move on to the next step from there. We also wanted to reduce human error, so we wanted to make sure that there was constant communication between the AR head-mounted display and the LMCC so that you had 2 people viewing the same information instead of just one, so it's 2 set of eyes that could notice anything that can go wrong. And so just to show off, this is what, I don't think our video is playing. But this would be what the breadcrumb mode would look like. And so the user would just select breadcrumb onto the hand menu and then walk a certain distance, and then as they turn around, they'll be able to see, eventually they'll be able to see that there are 2 breadcrumbs that are numbered, so you can know which one, kind of the direction you came in as well. Talking about doing step-by-step, we used basically these bars that were on the top right. So the instructions would be listed under task detail with whatever the step title was. We also would have progress bars to tell you how far along you were in the process. And as this was a team EVA, we also had the secondary astronauts progress as well, so that you as the first astronaut could keep track of it. We also listed the location of where all these switches were found. Was there on the suit? Was there on the UIA? So that then you also didn't have to remember what was going on. So we had kind of general ideas, but we really needed to figure out what's the best way of presenting that information. And so we created a set of studies where we ran about 50 people per to try and understand what's the best way of presenting information that's going to lower cognitive load, increase success rate, and then also decrease frustration as much as possible in the user. And so we had two main questions that we really applied to this headset. So the first one is, what's the best location to display alerts in an HMD? We wanted to avoid the issue of alert blindness that happens a lot in aviation. And is there also a way that we can display information in the HMD to optimize the user's performance? And so in terms of, for the first question of where the alerts is the best, where to put alerts, we basically presented users with alerts all over the screen in groups of 4. So every participant saw 4 alerts pop up while they were doing a simple task. What was really surprising in this case is that 82% of users did not notice any alerts. 18% noticed 1 alert, 0% noticed 2 or more alerts in the headset, which is a little scary to think about, as these alerts are important to notice. We're still doing some research as to why that happened. So the best thing we could figure out is basically to solve it for this project was to put the entire field of view, turn it into an alert when that happens, which is not ideal because we don't want to obscure the full field of view, but that is something that we had to do as kind of a last minute thing. We are looking to see what else could we do to make those alerts noticeable. In terms of knowing what type of information to display and how to display that information, we presented participants with either a task instructions all at once or task instructions one at a time. And though people who saw the task instructions one at a time had lower cognitive workload, they also had a higher frustration index. So we were trying to mitigate those two while we were implementing it. So we implemented an overall view of all the steps at the very beginning. So you have a list of what the major steps that you have to accomplish are, and then you can go to a step-by-step basis. And the goal then is you don't have to remember all the steps, you know where you're at, but you're still not as frustrated from having to, not knowing what you're doing throughout. So this is an example of how we implemented it. So before we would go on for the step-by-steps, we would show here are kind of the major steps with sub-steps in between. Here's what you're trying to accomplish within this procedure. And this leads us to our final design. I'll turn it over to you.
So our final design utilizes 2 main components, the LMCC Local Mission Control Center and the HMD heads-up display, which are connected through an EV telemetry server stream, TSS. So this is how our LMCC looks like. It utilizes a dual display to enhance the operation effectiveness. So the main screen remains consistent throughout the whole operation, and it displays the crucial information like the biomedical data of the astronaut and their vital signs. And the active screen can be chosen through the main screen based on whichever active tasks that the crew member wants to go into. And the active screen will display the selected tasks and be updated in real time. And as you can see, there's an instruction page that provides a brief overview of the whole procedure. So using the repair task, for example, at the beginning, the active screen will display an ordered list of the required procedures, and each step is outlined and updated as the DE progresses through the task. And when a task is complete, the LMCC user will click on the next task, and the previous procedure will be grayed out. So the procedure for egress and ingress has the same UI functionality. And when you hover over the step, the status of the specific switch can be toggled with color visualization showing the crew member what this current status is and if they've met that requirement. So this is the navigation or egress part of the heads-up display, and it features a progress bar which tracks the status of the whole egress procedure to provide the D with a greater understanding of the task. And they can tell if the task is updated in real time with color coding to show if the task is complete, not started, or in progress. And after completing the task, the user can raise their right hand and click next or go back to the previous step. So here just shows like a overview of the whole procedure. And then they'll just keep clicking through all the steps with the progress bar showing them the status and
Stop recording.
and then it's color coded to show like, oh, the O2 vent is currently closed, so they have to make sure that that's completed before they move on to the next step. So this is the navigation feature in the heads-up display, and there's a bunch of functionality that they can place different kinds of pins, like general, hazard, and breadcrumbs. And the blue ones there are the general pins, and when they're set, they display how far away they are from the crew member, and then the red one there is the hazard, which they might want to place at a point where they wish to avoid. And yeah, just really quickly, this is the geological sampling task, and it has like same functionality where after scanning, they can move on to the next sample, and it will tell them if the sample is abnormal, which they'd want to pick up, or normal. And they could also set like a specimen pin for that location, so they can come back and retrieve that sample. And we could also go over some like feedback and future steps if there's time, but thank you for listening. Hi, thank you for your presentation. It sounds like you guys did a great job. I was curious what tools you guys use to create your project, both the LMCC interface and also your different displays. Yeah, the LMCC was also created in Unity, and the HMD, we utilized the mixed reality toolkit, so that also came with a lot of features such as voice commands, like eye tracking, and hand menus, which we try to utilize in our design to just reduce the cognitive workload. Especially when we were testing, we realized that a lot of the crew members, they had like a lot of stuff like the scanner and the DCU, so it's really helpful to use the voice command and anything else that would reduce the complexity completing the tasks.
That was great testing that you did. I had a question about your sample size, how large your populations were that you were testing with, and if there were any other performance metrics other than cognition that you were looking at.
So we had, for each study, we ran 50 people. So the first one was within subjects, so 50 people per that study. And then the second one was split into two, so it was 25 per group. We mostly looked at cognitive, but we also had task completion time, task completion rate, how well our initial hope for the alerts was also trying to see if the way the alerts are presented, like would help remember what was actually being said. So we had, did they remember in one format versus another? We just didn't have a large enough sample size of people who actually noticed them to be able to do anything with it. But we were really interested in cognitive workload and frustration and whatnot, so that the UI was a little bit more intuitive.
Thank you, Team Daedalus. Next up, we have Team Jarvis from Purdue University.
All right, good morning, everyone. I hope we're all doing well. We are Team Jarvis from Purdue University. We're a team of officially 19 people, but in terms of active developers and software iteration, we've got about 8 to 9 people doing that. We've got mostly undergraduate students, freshmen, sophomores, with a healthy mix of graduate students in there as well. Now, Jarvis stands for Just a Rather Vital Interface System. In NASA tradition, we went acronym first, stands for later. And today we'd like to explain to you why we believe that interface is just so vital. So we all are familiar with the reason we're here, the problem statement, right? We've been tasked to create a set of interfaces that makes it easy and safe for mission control operators and EVs to complete tasks that are critical to scientific understanding, either on the lunar or Martian surface. Now, that's quite broad, quite vague. So we wanted to distill this down into some priorities that would guide our design before we just sort of sat down and started writing code. So the first thing is astronaut safety. Whoever we send into space, we want them coming back, alive and healthy, safe and well. The second is equipment safety, right? The equipment that EVs are going to be dealing with on the moon or Mars is going to cost tens, if not hundreds of thousands of dollars, maybe even millions. And so losing that, damaging that, not only impedes the mission, it also maybe makes Congress a little angry. So not damaging that equipment is quite nice. And lastly, of course, the completion of mission objectives, right? Whatever we set out to do, whatever scientific goals are in our purview, we want all of those to be completed as we return to Earth, so our scientists here can maybe analyze rock samples and look at data to understand things for future missions. So with that, I'm going to give a brief overview of what our system looks like. 3 main components, and we'll talk about what we designed first and why we designed it. So I'm a back-end and network engineer by trade and profession and by education. And so the first thing we ended up setting up was our gateway. Now the gateway acts as a simple man-in-the-middle server. It's quite straightforward, maybe 50 lines of code. And all this does is it takes messages it gets and sends it out to everyone who's connected to it. So if my HoloLens headset is connected and I've pressed a button somewhere, that'll send a message along to the gateway, and that'll handle the communication of such messages to other connected EVs as well as a local console. And the benefit of this is we can restart any device as many number of times as we need and still maintain a very simple, straightforward communication relay. And this removes all the difficulties that Unity and other native tools might pose to developing communications relays. Our gateway is perpetually online and handles all of this for us. The second is our LMCC, our Local Mission Control Console. And so we wanted our design to focus heavily on this. And so our presentation will focus almost entirely on the LMCC because we believe that if we can take the load off the HMD, off the EV of doing any tasks, we can enable those who are sitting at mission control to have high granularity control over everything going on in the EVA. And so the LMCC will enable that by a lot of intuitive designs that we've developed. And lastly, of course, our HMD. It's a very simple design, 3 straightforward panels. You've got a biometrics panel, a mini-map, and an active task panel with 2 buttons you interact with. This was probably the most basic interface we tried coming up with because we didn't want our astronauts doing anything more than they absolutely had to. Right? If you're on the moon, you're wearing a suit that weighs 70 pounds, 140 on the Martian surface, the last thing I'd want to do is hold my hands up and type on the MRTK keyboard that Unity renders. And so we try to keep our design quite minimal. So with that, let's talk about our design on the LMCC. We've got a dual monitor setup, so let's look at the left one. I'll call your attention over to the top left, where we have 3 sort of sub-panels, 2 of them dedicated to our EVs, and then 1 dedicated to a list of errors. So effectively, we took all our values off the telemetry stream, and we programmed in nominal and off-nominal ranges. So the second anything goes off-nominal, we display that up in yellow, and we prioritize it to the top of the list. So if we're doing an EV and suddenly oxygen pressure gets a little too low, well, we'll know. If there's an oxygen error, if the fan RPM is a little bit off, we'll know, and that'll be highlighted in red. And so as soon as this happens, the mission control operators can communicate either over voice or other methodologies, which we'll discuss, to the EVs that this needs to be taken care of and needs to be fixed. Over to the right, we have our task implementation, and we'll discuss that a little bit later in the presentation. So I'd like to now call your attention to the bottom, where we have our sampling interface. So part of this EV was, scanning geological samples. So the most recent rocks scanned by both our EVs are displayed. Their chemical contents are displayed on the bottom. And so the second anything is detected that is off nominal, for instance, if we find a silicon-rich sample on the surface of the moon, that'll be highlighted in bright red, and we can immediately drop a location pin there, and our LMCC will then be able to navigate astronauts back to that, or send a rover to that if that's needed, because that will be an interesting point of interest for later investigation. And so, speaking of navigation, let's talk a little bit about how that navigation interface is programmed. Over to the right, we have our mini-map. And so you can see that if any pin is dropped, there's some light green geographic pins that look kind of like Google Maps' pins. And so the second one of those is dropped, we can click on that, interface with it, modify its description, and send that over to the HMD. And so the second that our headset receives it, what will happen is it'll do the math to navigate the EV straight to that point. We can also edit the description. So if we realize that all right, there's more than just an interesting rock sample at some point, we can specify that. Our camera feeds are pretty straightforward as well. If we've got our HoloLens, we just pull the native feed off of that, and so we can watch live as our EV conducts tasks. If there's any difficulty interacting with augmented reality space or completing tasks, we can see that and not just hear that, and that gives us a bit more understanding and insight into the nature of the issue at hand. Rover feeds, also quite straightforward. We can monitor rover control from there with our native and thermal feeds. And then, of course, our geographic panel, which contains all the information we need for navigation. And I'll hand this off to Madeline to discuss our task implementation.
Thank you, Gurmahar. As he was saying, we've learned a lot about the importance of redundancy in spacesuit design. We wanted to include a visual aid so that we could guide the EV through the procedure more quickly and efficiently. So we implemented a task list in the LMCC. The LMCC sends tasks, information, procedures that we can directly go in and edit as we go over to the HMD, which will pop up on the HoloLens on a panel that the astronaut can see visually. We saw this in our testing, actually. Our audio and microphone was faulty yesterday, and we were able to directly send information over to our design evaluator with the lack of audio, so he could visually see what we were trying to say and we could maintain that communication. I'm going to pass this over to Mahir to talk about our computer vision.
Thank you, Maddie. So we use ORB feature matching to detect the UIA panel without any markers. Then we would place a marker over each button and highlight them as needed. So our goal with this is to reduce cognitive load. And as astronauts are preparing for egress, they might fumble with which button to press. And so we wanted to show and highlight exactly the button to press, reducing cognitive load and reducing the chance of critical errors. So I'm going to hand it off to Gurmahar to finish off.
All right, thank you, Mahir and Maddie. So let's talk about the advantages of our design, right? If we're going to the moon or Mars, well, why Jarvis? So the main guiding ideology, right, we saw our 3 design principles, but we want to stress how we tackled all 3 of those. So with regards to astronaut safety, right, we believe that with our LMCC, the panels that you guys saw on our left monitor, with regards to telemetry monitoring, biometric information, the second anything is a little bit off from what it needs to be, we know, and we can tell that over voice. And we believe it's quite useful for us. Our navigation system allows us to control where our EV goes. So in their field of view, if we want them to come back to the habitat, we press a button and say, hey, you're coming back. And if there's anything unsafe, they can make it there. We saw this in our testing yesterday when an oxygen error occurred, and so we navigated our EV straight back to the UIA to proceed with ingress. And lastly, again, our mini-map just makes it easier for us to do all this navigation, right? We can move EVs around as needed. And we can also, sort of segueing into equipment safety, if our rover is sort of driving off the edge of the map, we had an incident on Monday where the rover control was experiencing a lot of high latency. And so the rover almost made it into a ditch, and we were able to monitor that on our mini-map, and someone was able to sort of go outside and pick that up, make sure that we didn't damage it. And then, of course, our geographic pins, and then, again, rover control. The equipment that we have, the equipment that we're interfacing with, can all be sort of saved and monitored from our interface. And then lastly, mission completion, our task UI, like Maddie said, we can send over whatever task we want. We can modify that. We can change it on the fly. So if something happens, we need to do something new, we need to modify our mission objectives, we can directly edit that and control exactly what shows up in the field of view of our HMD. Our geological sampling makes it very easy to identify samples of interest. So weird iron content, interesting amounts of silicon, these are all things that we might look for on the moon. And so we can drop a pin there and come back to that later. Our UIA detection, as Mihira talked about, if we can intelligently detect components without needing to modify anything about the interface itself, then we can make it much easier for astronauts to interface with those physical hardware components. And that's how we tackle the mission completion, sort of a component of our priority list. We want to talk a little bit about user feedback. So we sent out a very early version of our LMCC to users at Purdue University. We set it up at a machine there, and we sent out a form saying, hey, we're going to give you very limited information on what you're supposed to do with this interface, and we'd like you to try doing something. And so we got a lot of feedback on how easy is it for people to send tasks over, how easy is it to monitor off-phenomenal biometrics. And we asked, well, where should we place this geological sampling interface? Where should we put it? And so a lot of the feedback we got was that, well, we should maybe restructure the way we display alerts. We should probably prioritize those that are off-phenomenal directly to the top. We should maybe have them blinking in order to make it call to attention to whoever's sitting at the mission control. And then we got some feedback on where to place our sampling interface, which was quite valuable to us. So just in summary, I want to wrap things up and then we'll open up to questions. I just want to talk about how we addressed each priority with our design. So with our LMCC, right, how did we tackle equipment safety? You have things like the rover out there, and you can monitor where it's moving, you can monitor the location, and you can make sure that it doesn't do anything off-phenomenal. With regards to cognitive stress, like Mihir said, I think the capstone of our cognitive stress reduction was that we could use computer vision to make it easy for any EV to move any component, intelligently detecting, and we would ideally in the real world apply this to other components. If we can use markerless detection to detect other interesting components maybe on the rover, then our EVs would have to receive, it would take a lot less time, a lot less effort for them to interact with important components. With regards to user feedback, right, the people who are designing the software aren't necessarily going to be the ones on the moon using the software, so getting feedback from people who aren't as engineering focused as us or maybe as involved with the development and seeing what they thought of it and seeing how we can modify our interface to be better. We incorporated that too with regards to our task list implementation and our alerts. And then of course, with our decision making, you'll notice that we focused a lot on our LMCC in this presentation. And that's because that's what we believe is the cornerstone of our operations. It's what enables the user of the HMD not to have a lot of stress, not to make many decisions. Like we said, there are 3 very simple panels in our field of view. And so ultimately, the mission control operators are responsible for enabling and making possible the entirety of the operation. Intuitive interface will make that, makes that much easier. Well, that's all we have for today. I hope we've all shown you why we've created just a rather vital interface system. And we'll open all to questions now. Thank you.
Hi guys, great presentation, really cool name for your project. My question was about your LMCC software again. So for this one, I saw you guys had a lot of information on there and a lot of different panels. I was curious about your thoughts on before, while you were designing versus when you were executing your test when you guys came to JSC. What panels did you feel like were most important, or did you think any were more helpful than others, and anything you might not have expected that changed during your testing?
Yeah, definitely. I think Maddie commented briefly on yesterday. The audio comms that we were given were a bit faulty. And so the task list panel that we had, we can modify that procedure. And so when Pat, the guy who was our design evaluator, was wearing our headset, we just typed in a message saying, hey, Pat, can you hear us? Can you just confirm visually or by audio? And that's sort of how we immediately realized, okay, well, audio isn't working. Let's go communicate and fix this. I think that was probably the most versatile one, mainly because it provided failure redundancy, which we're realizing is a lot more valuable than we previously envisioned.
Awesome. Thank you, guys.
Yeah, great presentation. In fact, your priorities are exactly how we execute like ISS today in the Mission Control Center. That's the same priorities we have to walk through all the time anytime we have an issue. So yeah.
We got them from our mentor at NASA. Credits to
Good.
Allison Bollinger
Good.
for that.
Yeah, that's very good. Question for you on the, and maybe this is for a lot of the teams too, is your navigation, is it based solely on the IMU? Do you have a redundancy there? Because there is going to be some drift and stuff there. How do you address that for your breadcrumbs or anything else you're doing?
Right. So I think there was a DCU, is it, that broadcasts out GPS coordinates. So there was some drift on that. There was maybe an issue with signal reflection off the silo. We did have a plan for this. We didn't realize that would be a problem when we got here, but as soon as the first test day happened, we realized that there was this drift. So there were, while we don't have that built in currently, we did sort of mind board, brainstorm about how we would solve that. So right now what happens is you pull the coordinates, which are our universal transverse Mercator, right? And so you've got the current position, your target position, you can compute a straight line or intelligent navigation path. If you have any drift, one way you can do this is, and this was suggested by one of our team members, Benji, who's out there in the crowd, if you calibrate your starting position in the rock yard or wherever your EV site is and you face at some north heading, you can use the accelerometer in your device and use that to compute over time what your heading and your position is. And so you can convert, if you know the, UTM positions of your starting place, you can then compute your UTM over time as a function of acceleration and then use that to intelligently navigate. And that would reduce reliance on your DCU and GPS entirely, which I think would be useful on the moon because, there's no GPS, right?
Thank you, Team Jarvis. Well done. All right, welcome Team Suits from Columbia University.
Hi there, my name is Jonah Aiden.
I'm Angela Bai.
I'm Matthew Ruskowski.
And I'm Moises Mata, and we're Team Suits from Columbia University.
Our team is comprised of 12 members, all undergraduate students at Columbia University, and we are part of the broader Columbia Space Initiative, an engineering club of over 200 members.
All right, so very quickly on a project overview side, and how do we tackle this job of lowering cognitive load on menial tasks so that astronauts during their EVAs can focus on more productive issues? So our solutions to that, we decided, was a clutterless UI for our head-mounted device, along with a localized mission control center that could access data on a much deeper level and then send whatever was necessary at that point in time to our user. Very briefly, on the technical side, our HMD is made in Unity using Microsoft's MRTK3, as well as our LMCC being made in React JavaScript with the Mapbox API and the Windows Device Portal for live streaming.
Our system architecture centers around a back-end server made using Fast API, as Moises said. We're then connected to the LMCC and HMD, and we're receiving data constantly from the TSS.
So very quickly, back onto the HMD design. We designed everything to be discrete and modular. So what does that mean? Upon startup, the user will only notice a mission timer in the top left corner. However, all other functionality is tied to a hand menu. This hand menu is tracked with your palm facing up, and then using your other hand, you can click any buttons as you see fit. Upon clicking a button, the user will notice a window for the respective tab open, and that is originally set to follow the user. However, using that lock icon we see in the top right corner, the user can kind of place that wherever they would like in space. Using this design, we kind of thought that the user could have as many or as little windows as they like, and also kind of organize that in whatever orientation they see fit.
For egress and ingress, our design included a UIA display that highlights whichever switches need to be flipped, and this way it provides visual guidance to the user as they complete the procedures. For equipment repair, procedures sent from the LMCC are displayed step by step with buttons to move forward and back. For navigation, a mini-map of the Johnson Space Center rock yard is accessible to the user with pin-dropping functionality that appears on the map on the LMCC. The astronauts' vitals are viewable through a hand menu with the ability to toggle between EV1 and EV2. Other accessible information includes spectrometry levels and a compass for navigation.
For our mission control, we have a constant and focused display. The constant display has some of the most important information, such as our different video streams from the rover or HMD, as well as a mini-map and any other vitals that we might need. As the mission goes on, you can access the different focus tabs so you can get more detailed information for the various parts of the mission. We achieved this using Mapbox, which is how we got a custom map of the rock yard, and then React.js, which is pretty industry standard for sending data real time.
Our backend server, as we stated, is made with Fast API. It's constantly scraping TSS data and saving it in local JSON databases on our computer. All that data is then processed and accessible from the HMD and LMCC via 17 endpoints.
Alrighty, very quickly, you can all imagine, as I'm sure you've all encountered, this process is filled with a lot of trial and error. So here we have some problems and some specific solutions we took to take them, and we'll take you through that.
Our original design mock-up for the HMD was an Ironman-style heads-up display where all the information is constantly locked onto the user's field of view. In user testing, we saw that this made it difficult to see the task at hand and really focus on the task at hand. So to solve this problem, we created a modular hand menu to allow the user to quickly access any information and place windows where they see fit.
Our original mapping solution used the TIFF file of the Johnson Space Center Rockyard. However, we wanted to include the ability to zoom and pan to kind of give the user a more intuitive mapping functionality. So we decided to use the Mapbox API on our LMCC to allow for this kind of updated UI and user experience.
For our procedures, we originally had a really simple approach. We had all of the information in regards to that stored locally on a static page, but then we realized as the mission goes on, you might want to change or edit things, so we created a server that allows us to add, delete, or edit different parts of the procedure.
Our first mapping implementation or navigation implementation was a simple point A to point B direct line approach. However, we realized that this would often take the astronaut over hazards such as the mound in the middle of the Johnson Space Center Rockyard. So in order to account for this, we created a graph of the Johnson Space Center Rockyard with nodes and edges, and then changed the weighting of those edges to kind of account for what would be best to walk through and over. And so we kind of like killed every edge that went over the mound in the middle, and then we ran Dijkstra's algorithm on that graph to kind of calculate the shortest path between two nodes, accounting for all physical features.
Once again, going back onto changing things dynamically and not having things hard-coded, originally we did have things like IP addresses, EV room numbers, team IDs, all hard-coded, which, I mean, really made things a headache trying to rebuild and recompile, redeploy to the HoloLens. So to fix that, the LMCC team was able to hold a database of basic configuration things, all our Macbox key, our IDs, and so on. And through that, we were able to interact via the LMCC and just grab those data on the HMD and really make things a lot more flexible, which really helped contribute to us doing well on test day.
On our first day of testing this Monday, we realized that we were heavily reliant on constant TSS connection in order to run our mission. This gave us a lot of headache when the TSS stream was overloaded with data packet submissions and was kind of faltering. So in order to introduce redundancy, we introduced between Monday and Wednesday the saving of procedures on device as kind of a backup measure to ensure that the mission can be completed even without a strong connection.
For future development goals, we hope to implement a breadcrumb navigation system on the HMD, as well as an image capture capability on the LMCC side of HMD and rover streams. We also, based on feedback from user testing, we believe that it's important to have an emergency shutdown button, which we hope to implement in the future, as well as voice and gaze control. Finally, we'd like to have a more detailed graph for Dijkstra's pathfinding algorithm.
Okay, so lastly, I'd like to speak about some of the outreach efforts we made here at the team. We were very pleased to be able to reach out to a large number of younger students and community members in New York City through our Space Initiative's biggest event of the year, Spaceposium, which is pretty much just a day full of like space-filled fun and outreach activities. Our team specifically presented in a poster session in which we were able to talk about UI design principles, exciting possibilities that are now possible with AR technology, and of course demos of our HoloLens device, which was super exciting for the students. Our team also wrote a presentation that was tour rotation later on in the day, which focused on the history of programming during the Apollo era and how NASA really pioneered that. And it also ended with a coding activity for an Arduino car that could navigate a maze on the ground. And that's going to be it for us today. We open the floor for questions, and thank you all for your time.
Great presentation. Thank you so much for all your work. I saw that you kind of had like the global awareness and then zoomed into the map. What made you choose that option?
Yeah, so we're very familiar with navigation through like Google Maps and Apple Maps, and we knew that our users would enjoy that functionality too. So we decided to make kind of a mapping solution that allowed for a lot of kind of future development if we wanted to include more pins and pop-ups and layers to a map than we would want to do on kind of a static image map.
Yeah, just out of curiosity, on your user interface, it sounded like maybe in the beginning it requires two hands to get started, but then you can tag something or lock something on the screen. Is that true?
Yes, so in the beginning, like I said, the only thing that we have is that mission timer. However, imagine you almost like bring up your cell phone, you're going to have a bit of a screen next to your palm, and then using your opposite hand you can click, but then once you have the window in front of you, that can be done with one hand, locking things in one hand, and so on, yeah.
Thank you guys for your presentation. I wanted to ask a broad question. So based on your design and then after your testing, are there is there anything that you learned about like lunar surface EVAs just like along the way and like while you were doing your testing? Do you feel like there's anything that you would have changed or done differently?
Yeah, I mean, I'll start and I'll pass it off to you, Jenna. I mean, first coming in, and I feel like growing up, didn't really appreciate all the engineering work that went into an EVA and how many things had to be, I mean, working flawlessly, right? And then there comes the added extra component of teamwork, which honestly we became more aware of and more flexible with coming into test week with us functioning with another EV.
Yeah, one thing I'd say that we learned through development was how important astronaut autonomy is, and especially during our testing this week, we realized that we were kind of reliant on the connection between the HMD and the LMCC and voice communication or sending procedures back and forth. And we have decided that in future iterations, we would like to emphasize the ability of the astronaut to complete the mission without any connection to the LMCC, and the LMCC should just be there for support.
Well done, Team Suits. Next up, we have Team RISD from the Rhode Island School of Design and Brown University.
So hi guys, we're RISD Suits. We're a collaboration between both RISD and Brown University. So this is our agenda for today. Just quickly flash that. And yeah, introductions. So my name is Michael Wang. I'm the PM for our team. And here we have Kea Sham, our designer. We have Martin Ma, who's our chief developer. And we got the team lead for LMCC, Lin Yu. And we have team lead for our AR segment, Sunju. Danielle, who's our senior dev, and Seik, who's going to be part of our senior dev team as well. So our team management structure basically is as shown here. We have project management who's going to be directing and making sure that everything is going on time, and we have the rest of our leadership team who's going to be coordinating tasks and distributing it among their team members. our timeline for this year essentially went like this. We will discover what our parameters are for this year, and then we'll go into our research, prototyping, user testing, and then we'll iterate our designs and development, and then do user testing. This will all interchange as we learn things from our testing and make sure that our changes are great for whatever our team needs. Keo will now talk about our design for this year.
Hi, so our design team was led by a few key guiding principles, as you will see through many of our features. For egress, we really wanted to make sure that our user always knows what they are doing and confirmation across steps with progress tracking. And so we provided that with progress tracking bars, and also a lot of our steps are automated, and so the user will always see whether the step is in progress or completed on that panel. Our wrist menu provides streamlined access to all features just with the flip of a palm. Here you can see that there are also shortcuts to provide quick access to features that they would need on the regular, or features that they would require in emergency scenarios, such as returning to the lander or beginning ingress procedures. With navigation, we wanted to make sure that they were always aware of their surroundings at all times. So that means stations, hazards, knowing the location of themselves, the rover. With all of these features, we also wanted to provide flexibility so that they could adapt to their surroundings, which means that they could add custom POIs or hazards to anything that they notice in their surroundings while they are in the EVA scenario, and record anything outside of what they may have pre-planned for that mission scenario. We also wanted to make sure that they can record every single detail of what they are seeing. So when they are dropping a POI pin or a hazard pin, they can record image and voice notes into those points themselves, which can be location tagged and also recorded on the LMCC end. With equipment repair, we wanted to make sure that there's clarity in communication. So here also, we wanted to make sure that they are following tasks that are sequentially presented so that there's reduced risk of error. We also want to make sure that this is consistent with the rest of our interface. So if tasks are provided in the same way that they are in egress. And with geosampling, we wanted to make it intuitive, so it follows an automated flow. As soon as they scan a rock with our RFID scanner, picture-taking capabilities automatically begins. And with this, they can record the sample, the elements within the sample, and also attach voice notes to it so that they can comprehensively track everything that they are seeing. Our LMCC unit acts as a second pair of hands, eyes, mind, and ears to our DE. Anything that they may not be able to pay attention to, LMCC does and assists them through all of these tasks. We have this with a map that syncs with what the DE sees on the heads-up display. We have notifications that give them information of everything that is happening on the DE and rover end. Task list that comprehensively manages everything that our DE needs to do, and telemetrics which keep them aware of everything, any emergency scenarios that our DE may come across. Some key features within LMCC that we would like to highlight are draw path, which syncs with the map that the DE sees so that the LMCC can navigate them across stations while avoiding obstacles and providing them with the most efficient path. We also have files, so any picture or voice recording or geosample that is recorded on the heads-up display is stored within LMCC. This is also where they can tag or flag certain geological samples for further study. And here's a demo of some of our LMCC features. Rover commanding is made easy through the notifications and through that video display. We can also see rover movements on the map, and geopins can be dropped for wherever the rover is picking up rocks. Our telemetry stream allows us to quickly initiate abort scenarios. So with any error that is seen, an abort notification can immediately be sent to the DE on the heads-up display. And we wanted to make RD's movement also very simple. And so we created a vest that could hold all of the units of our heads-up display. So the processing unit, the battery pack, our Raspberry Pi, which was giving us our video feed, all kept strapped to the body so that they can move around the field easily. And now I'll hand it over to Martin to talk about development.
Okay, so now I'll just briefly go over the software development aspect. We developed our AR application using Unity, and we deployed it to Magic Leap 2, which is our choice of a head-mounted display device. And we developed the front end of our CC using React with TypeScript, and the back end using the Flask framework in Python. And we're also using a Raspberry Pi with a camera module that serves reliably a video feed of the user from a slightly different perspective than that of the camera on the head-mounted display. And here are the simplified diagrams of our system architecture. So for our AR application on the left, this is with emphasis on the communication aspect. And so for networking, it continuously pulls data from the TSS server as well as our LMCC backend. And also it uses a centralized state management script that defines kind of like the state transition between different views of our UI interface. And for our MCC, we also fetches data constantly in the backend from the telemetry server as well as from our AR application. And for the front end, we are just displaying directly the video streams that we get from both the rover and our Raspberry Pi. And just some notes on the hardware side. We're using Magic Leap 2 this year, and compared to the HoloLens 2, which we've been using in previous years, it provides a slightly higher compute capacity as well as a wider field of view. And as Kaya has shown in the previous slides, we use a tech vest that holds all the components of our, including the Raspberry Pi and the power banks. And also we kind of devised a custom cooling solution to mitigate the overheating problem that we observed during the first test date. And I'll hand over to Michael to talk about user testing.
So in true RISD fashion, we try to do as much testing as we can in order to find the best middle ground between the design and completing our objectives. Oops. Yeah, so usability testing starts from essentially as soon as we're done with some of our Figma graphs and user wireframes. Then we'll go into collecting some subject pools. They basically range from people we can find at our college, mostly people who have high amounts of experience with both UI design. We also try and mix in there a couple of people that have nothing to do with this, and just to see like how they interact with the design and where they go first. We also try to do some human metrics. We'll make them sign some stuff just to make sure we can release this data eventually if we need to. We also went to some of our professors who are highly experienced in this field. We have Brian James and Hillel O'Leary. So they identify a lot of different things that we need to test and make sure that we change to make all of our interfaces a lot more clear. We also did a lot of outdoor testing. Unfortunately, we're from Rhode Island, and during our testing, the weather outside was a nice, 70 degrees Fahrenheit. So we did not anticipate any of the overheating issue, but we used the Magic Leap to be able. But like using that same lighting condition, we're able to find that some sort of shielding needs to be done, and we realized that we have a feature in Magic Leap called global dimming that we're able to use to dim the entire display to make sure that we are still able to see our interface while being able to essentially wear sunglasses underneath our display. In the outreach section, we did some campus awareness to make sure people understand like what we're trying to do here in in an informative manner, and try and do some recruiting to jumpstart our program. We also have a lot of social media presence. We post about once a week with pictures and information of what we have completed for that week's meeting. This allows us to reach out to more people in our campus, and just try and get a bigger team for next year. So for our final remarks, a lot of things that we learned this year are that during recruiting, we realized that a lot of people are here to learn because we're a college. So there's a lot of varying degrees of learning that has to be done for our team members in order to get on the same level and same page for our softwares. We also had some initial work dynamics things that could have been better. That's on my part, honestly. And new hardware difficulties such as the Magic Leap, just learning new pieces of software and our capabilities. Also heat management that we found out very acutely when we got here. We also have some cut features that Martin will talk about.
Yeah, so one feature that we did not get to implement is the active navigation mode, which basically when the user is navigating to, for example, a station, this overlay will show up with an arrow in the top center that points to the station, as well as a minimap on the top left corner that shows a path that's drawn by the MCC. So while this is mostly due to the time constraints, as well as our lack of testing over position and direction related data. And in future, we will probably try to find a testing site that has a terrain that's similar to the real testing site, and we're gonna just recenter our map to the testing site to do all this testing before coming into Houston.
All right, so that's the end of our presentations, and we're going to open up to questions.
Great job, RISD. Myself, Tim, we just got back from field testing in Arizona, and one of the things that we realized is that there's a lot of aspects of testing in real time that impact your design. And what were some of the aside from the heat management, what were some of the unexpected challenges of being in the field analog scenario in the Rock Yard?
I guess some of the challenges, well, the communication between our AR application and the backend for our MCC was definitely it's because when we tested back in the school, we had very stable Wi-Fi and everything, and here it's one thing, for example, we had planned on getting device stream from the headset directly, but using the built-in functionality for this device streaming, it's there's lags and also quality degradation. So that's why we had the Raspberry Pi with camera as our backup plan. Which worked pretty well. It's able to provide stable video stream for with I guess acceptable frame rate. So I guess those are some things that some of the challenges that we faced due to our testing condition being slightly different from the real testing site. And in the future, we will definitely try to control those variables when we're back at school testing to reduce uncertainty in the real testing scenarios.
Really great job, guys. I loved hearing your presentation. One thing that was really exciting to me was that you guys used the Magic Leap. So I know you talked about your reasons for doing that, but I was wondering if, as part of that decision, you'd use other AR headsets before, and then you guys liked that one, or what was another decision in that?
We came across the Magic Leap when we when we heard about it from last year's competitions that some teams are thinking about using it. During the off season, we were doing a lot of research on whether or not Magic Leap will actually be a helpful addition to our team. And based on the hardware specs and the ability to do global dimming, which has been very helpful for an outdoor environment, we decided to first take a loaner unit out. Yeah, so just PSA, Magic Leap has a loaner unit program, so if you need someone for like around a month or two, please go ask them, and they will provide something for you just to try things out. But yeah, so like all of those features added together with an x86 hardware architecture, we're able to get a lot of things put on much faster than we were able to do with an ARM architecture such as the HoloLens 2. On top of that, we also able to get a higher fidelity image from our projection system, and also having the compute unit on a separate device with its battery also lighten the load on the head of the individual who will be wearing our device. So all this combination of factors led us to decide to switch over to new hardware.
Awesome. Thank you. Well done, Team RISD. Next up, we have Space Bears from UC Berkeley and Baylor University.
Hello everyone, I'm Rojan and I'm here today with Isaac, Kai, Zixun, Zoe, Yunting, and Aaron from University of California, Berkeley, and Advika from Baylor University, representing Team Space Bears. Before we begin, I'd like to start by proving a point to you all. So, imagine Isaac as an astronaut. He is about to go on a mission, and on this mission, he will need a clipboard for managing mission details, a device for communication, and also a toolkit for managing repairs. Now, the complexity of this could be a lot when on a mission. As you can imagine, while on a mission, this would be too complex for an astronaut. So, managing the while as we so going through the mission, we would want to eliminate the need for using the hands of the astronaut. In order to do this, we have designed a LLM-driven immersive augmented reality user interface that is voice-controlled and frees the hands of the astronaut to perform more crucial tasks.
Yeah, so my name is Isaac Gonzalez, and I'd like to bring your attention to two different designs in AR. So one is the traditional AR design, which usually requires hand gestures and eye gaze to manage the interfaces, along with like UI that tends to clutter like a user's like field of view. Our design, which we have named ARSA, focuses on a non-intrusive like UI design where we keep all of the displays outside at the edge of like the AR of displays like of dimensions, and we also have a chatbot named ARSA who we are capable of speaking voice commands to, and we have ensured that ARSA will bring up these like displays out also at the edge of the AR's display dimensions. So I will now play a video a demo of our UI.
Now, imagine you're the astronaut about to begin the mission. After opening our assistant, you can view your current status on the top menu. You can also easily hide and display the top menu by interacting with Ursa, our voice assistant. Our system is similar to the interface of Google Glass, where the display is non-intrusive. We keep most regions on the glass clear for the astronaut and rely on voice for command instead of gestures. Now, if you want to check your suit's data, you can say, Ursa, open my suit. The underlying function call is done by a large language model, Gorilla, which is developed by another UC Berkeley lab. For example, when you say, Ursa, check my heart rate, the LLM will call a function that gets the heart rate and respond in a voice message about your heart rate and whether it's within the. Once you start the egress task, Ursa will instruct you on how to interact with the UIA dashboard. For example, Ursa will inform you to switch the UIA oxygen vent to on. With the UIA tracking algorithm, as the video shows, the area to be interacted with will be pointed out. The same flow applies to the ingress task. Now, you're going to the work site to conduct other missions. You can say, Ursa, open map. Then you can navigate to station A on the map by saying, navigate to station A. Ursa will provide visual aids to help you reach your destination. When you're at the station A, use XRF device to scan the rock. The information about the rock will be shown on the HMD. If you want to check the rover's location, you can say, Ursa, where's the rover? Ursa will tell you the rover's GPS location and place a visual overlay onto it. You can also check the rover status by opening the rover dashboard. Ursa, open the rover dashboard. Ursa will display the rover's basic information on the dashboard as well.
Yeah. So after seeing the demo, I believe everyone get a sense of our UI. This is our overall structure of the project. The center of it is the AR UI interface with non-intrusive design. The astronauts will interact with the UI using voice control and HoloLens headset. So this interface is connected to a large language models. It will take in the voice-to-text commands sent by the astronauts and call back the functions to the head-mounted display to actually manipulate the UI. On the other hand, the UI is also connected to a rover tracking algorithm, which is called DTDD localization. It uses YOLO to the bounding box detection and the DTDD net to get the camera feed from the UI interface and send back the actual rover position. So the challenge that we are trying to solve here is to enable accurate 3D object tracking in mobile AR interface. And the digital twin that we use means that the replicas of objects in AR and VR space. Our solution to this problem is consisted of 3 parts. We developed a DTDD1, which is a data collection pipeline. It was originally focusing on household objects. And for DTDD2, we developed a transformer-based 6 degree of freedom pose estimator. For NASA suits, we specifically developed a RGBD datasets for robots, specifically Leo rover. It is using Z2 camera to capture all the data, and we train the algorithms to post-estimate the Leo rover. So here is a tracking demo. Basically, we'll overlay a green circle on the Leo rover that helps astronauts to identify the location in Mars. It is using DTDD nets, which is a centimeter level digital twin post estimation. This will really help astronauts to be able to see the Leo rover in Mars rather than just getting a more inaccurate GPS location of the Leo rover.
Okay, so as you guys heard before, we decided not to use gesture-based controls. So what exactly do we use? Well, we use a voice-controlled large language model. And because when you're on Mars, you can't make API calls over the cloud to OpenAI, this large language model runs locally on the LMCC. So this is an example of how it might work when you're trying to call a function on the HMD. So the astronaut might say, Ursa, open the map. Then our voice assistant, Ursa, on the HoloLens will take that voice input and transmit the text to Gorilla. Gorilla is the large language model that we use, and it was developed by a different team over at Berkeley. And it requires about 12 gigabytes of VRAM, so we're able to run it on our LMCC. Obviously, there are some hardware constraints there, but hopefully in the future we can reduce the size. Gorilla then will call the proper function, and a change will appear on the HMD. Additionally, the LLM can be used to control the rover. So the rover functions were developed using ROS2, and there's a variety of high-level toolkits like SLAM and path planning that we use. And so just like with HMD, Ursa can make function calls for the rover, which I'll show you a video of now. Ursa, return to base. So now, Gorilla will call the function that exists on the rover that allows the rover to navigate back to the coordinates 0, 0, 0 in its own frame. So there we go.
Perfect. The rover is at home.
Thank you, Kai. So Spaceverse in total has done 7 outreach events across California and Texas. Our aim in these outreach events was to inspire the next generation and teach them more about augmented reality and AI and how it is used on projects such as the Suits Challenge. We were also given the opportunity to participate in the NASA Texas Space Grant Conference, where we were able to get lots of valuable feedback, which we hope to include in our future improvements and designs. This is an overview of our team from Baylor and UC Berkeley. And we'd also like to shout out our sponsors and our advisors, Dr. Sherry Jergu and Dr. Alan Yang. And please follow us on our socials. Thank you so much. Yeah, are there any questions?
Okay, great job, great presentation. I like how you consider a lot of things, and you guys win the award for having the most animals in your presentation for gorillas and bears. But one question for you is we're still, I think, a little bit in the infancy of voice control, because I know I struggle sometimes with my Texas accent that I have with recognizing. What was your fallback plan if you do? And I've noticed you detected some different accents on your team. So how do you handle that situation? Does the software, do you have to do any kind of adaptation to each person? How's that work?
So yeah, that's actually a good question, because sometimes we found it hard to detect some words. And one way we try to do this is that we can put similar sounds of the specific words. For example, if like our assistant is called Ursa, and we can put like Elisa, Usa, or something like that, and they will all be recognized as Ursa. So that is one of our solution. And the other solution is that LMCC is always monitoring the astronauts' behavior as well as the camera feed of it. So if they can recognize what the astronaut is trying to do, they can send the function call directly back to the UI interface.
Yeah, just to let you guys know, I don't know if you realize it. I know we have a couple of former crew members in the audience here, but when a crew member goes in a spacesuit, they are reduced pressure, and that actually changes their voice. It's kind of funny for us sometimes to hear the crew member. We're so used to talking to them one-to-one. When they get out in the spacewalk, they sound a lot different. So that's one thing you might consider for that too. Yeah. Thanks, great job.
Great job, guys. I also wanted to ask a question related to the voice control. I thought it was really cool that you guys added the remote rover voice control so that you could move the rover. Is there any decision behind that made you guys want to add that feature to, other than, I thought it was really helpful to the crew because, hands-free voice control. Any other decisions behind that?
Not really. I mean, I think it's more of like a proof of concept that the LLM can be used to control more things than just the HMD, right? So let's say as an astronaut, you might have the rover following you around and maybe some repair equipment like a robotic arm. You should be able to control like all of these things whenever you want, just by using the LLM and making these voice commands. So that's why we developed using the rover for that. But yeah, hopefully that answers the question.
Yes, thank you.
So you mentioned you used the Gorilla language model. Why did you choose that? And also, is it at all cloud-based?
So we chose it because it was developed at Berkeley, but also because it's relatively small, right? We use a laptop for the LMCC, and although it does have a 3080 in it, so it's not your average laptop, it's something that like you should be able to carry around, right? You don't want to have to rely on an internet connection to be able to use the voice control and use the LLM function calling. So that's why we chose to use it, because it was accessible and it was functional. So
thank you.
Great job, Space Bears. We are going to take a short break for our in-person audience. This would be a great time to move around a little bit. We will resume promptly at 11 a.m., so in about 20 minutes. All right. Thank you.
Rishi, we can't hear you. As we continue, Avi, do you want to just cover this slide? Avi, since technical issues, would you mind covering?
We can hear you. Sure, I can go over this next slide. So, yeah, for A-Star, one of the main areas that we wanted to focus on was improving accessibility as well as support functionality during suboptimal EVA conditions, such as rough terrain. As such, we use spatial processing data from the HoloLens's Windows device portal, as well as a height map to generate a data set of the rock yard, which was then processed by the A-Star pathfinding algorithm, using terrain heights to basically form a cost for each route. With each route having a cost, we were able to provide a near optimal route for the DE to traverse to their destination, such as from geological samples to the rover or to the comm tower and beyond. These waypoints were then placed on the HMD heads-up display to assist navigation. And to tackle potential visibility issues along this path, Isha will tell you about our software solution for glare reduction.
Okay. Basically, we wanted to create a very general system for... Oh, next slide. Yeah. We wanted to create a very general system for removing visual errors, and the special case we chose to test this was camera flare removal, like on the lens. And to do this, we had a pipeline where you sent the frame to a classifier, which would decide what errors there were, and then we would use a post-processing shader to remove them. While the classifier did work, we had some issues with running post-processing shaders on the HoloLens, and so we ended up in the actual test replacing it with a physical device because sometimes software just won't cut it, and so we created a like a visor out of camera or car tint, and that worked actually very well during the test.
Next slide, please. So, as most people have mentioned, one of the main challenges with this project is minimizing cognitive load. So, in order to ensure that our design did this, we devised a intense human-in-the-loop testing procedure, which was intended to, first off, give us feedback on our UI, and second of all, find a quantitative way of measuring that cognitive load. We were able to hold one testing session, only one due to logistics, and during that we got really good feedback on our UI and were able to improve our design, and that really showed during the Rockyard session.
Speaking of that Rockyard session, we tested in 2 different times, the first time and the second time, and during each of those times we discovered several different things that were of note during each session and several different flaws and errors that needed to be fixed. During the first one, we noticed major connectivity issues, which we were able to effectively rectify by the second session, which only had a minor map error, and were able to complete testing very successfully and to good results.
Next slide, please. All right, and on the topic of our results, we had some results up there, but we also had some excellent feedback from our design evaluator, Brianna. And some of these include a simple and effective UI where the elements are out of the way, so our view is not obstructed from the middle. And also, it required minimal training to use. It did not take long for our design evaluator to get used to the UI and understand what to do. Our automated warning system, it would send warnings automatically as soon as they popped up. And they would appear in the top left. It would be easy to see due to a red color coding. And because of this, it would decrease cognitive load and allow the astronaut or whoever's using the device to act on the warning immediately rather than worry about how to see the warning. We also displayed priority telemetry information. That way they can focus on the vital information and not have to sift through a lot of information to find what exactly is going wrong. Additionally, we also have a robust communication system. When our voice comms went down on Wednesday, we were able to continue giving our design evaluator tasks throughout the duration. So we would upload tasks in our task list. She'd be able to read them, and she would be able to continue doing what she needed to do until we got voice comms back up. We also have a picture taking feature which allows geologists to examine the samples that the EVA user was examining. And our system also integrates well with other workflows. This would allow us to also help other teams in case they needed some assistance from our end.
All right, next slide, please. So during this project, there was a lot of lessons that we learned over the testing period. Our product performed very well. After some modifications after Monday, on Wednesday we were able to do everything that we wanted to do and work through some challenging, in situ situations. There's a lot, though, that we still want to optimize and improve if we were to make another generation of this. One of the things is that because we used red for the warnings, which is pretty obvious why we did that, we also used red for the pin system. And this led to some confusion because the DE thought that those were like areas to stay away from instead of areas to go. So in the future, we would look at like NASA color coding guidelines to make that more intuitive, and avoid that confusion. Another thing is that we want to definitely do more human-in-the-loop testing. It was very hard for us to collaborate, being from all these different universities, and so we didn't get nearly enough data to have any statistically significant results. So doing more of that and tweaking our procedures would be a great step forward. We also had some suggestions from our design evaluator, Brianna Sparks, that we would definitely want to implement in the future. Things like adding vibrating pads on the shoulders and torso to help with navigation in case both voice and visual were down, or an audio cue to indicate like an emergency or something along those lines. This would add to like our already functioning and strong product to create a system that would really, really help in the future to increase safety and efficiency of these EVAs. Lastly, I just wanted to give a really big thank you to our faculty advisor, Professor James Palco from UC Merced, as well as our NASA mentor, Caleb Cram, and our design evaluator, Brianna Sparks. All of them, enabled us to be here. This is an amazing opportunity, and we got some really good feedback. And yeah, so thank you for that. And with that, we'll open it up for questions.
Hi guys, thank you for your presentation. I had a question about, or more of a comment. I like that you guys thought about using the lens flare processing for those harsh lighting conditions. I wanted to just ask what sort of thought process went behind that.
So basically, they talk about in the Artemis missions that lighting is really poor on the moon, and we thought, if you're in a critical mission, you really can't afford to be blasted with light in your face and not be able to see your working environment. So if we were able to fix some of that at a software level and even improve it a little bit, then that would just be fantastic.
Thank you.
I have a follow-on question to Katie's on the lens flare. So what were you measuring? Was it the difference in the extreme white light to the background? Were you looking at just binary pixels and black and white pixels? And was there anything else that you had mistakenly identified as a flare that was not a flare?
Yeah, so actually in our proof of concept, we ended up, to address that last question first, we ended up identifying straight lines because that does a reasonably good job of getting the flare, and it's very fast if you can, because it's just a couple of vector operations to get a straight line, and then you can inpaint it. And unfortunately, that will sometimes make errors because obviously there's straight things in your view, and it works most of the time, but yeah, there are definitely some problems. And then, yes, you're definitely right. Taking the max pixel value that's problematic was what we used to as a metric.
And so did you recognize other things in the environment that were not flares, and what were they?
Yeah, one of the things was we had a lot of white text that was a little bit problematic, but in principle, you can get the frame without the text and process that. But yeah, overall, it did a pretty good job of picking out just the flare and not messing anything else up.
Thank you. That's a brilliant idea.
Thank you for your presentation. I was curious about your cognitive load from the perspective of what changes you made based on your human interaction testing, and what were the results of those changes?
Yeah, so the main change that we made was to our emergency system. The way we tested was based off of doing various things with the response times to those like emergency warnings and things like that. And what we realized from our testing was that occasionally there would be this huge, like we'd send the message and most of the time they would see it, but sometimes there would be a huge lag in the amount of time it took them to even see it. And so what that told us was that we needed to make our emergency procedure or our emergency notification much more obvious. And I think that really paid off. One of the things that our design evaluator specifically told us was that when the O2 error happened in our test on Wednesday, she didn't have to do anything. She just stood there, and then all of a sudden, warning, and then tasks showed up. So that was one of the main improvements that we made based off that testing.
If I could just add to that, a specific feature that greatly helped was we added a red vignette around the edge of the field of view, which immediately helped all the test subjects identify there's an error right away because it's very, very difficult to miss, unlike a simple text box.
Awesome. Thank you.
Thank you, Team Cartographer. Obviously, a couple of their members had to fly home early, so we just wanted to acknowledge you guys' flexibility and dedication to this challenge. So thank you for making your exit pitch work today. Next up, we would like to invite Team Mike from Embry-Riddle University.
Okay, so we are the Embry-Riddle team, Team Mike, which stands for Mixed Reality Information Kit for Exploration. I'm Miranda, I'm the team lead, and I'm an aerospace engineering major.
Hi, my name is Joyce. I'm the human factors lead, and I'm a spaceflight operations major.
Hello, my name is Cole. I'm a computer science major, and I was the LMCC developer.
Hi, my name is Joseph. I am an engineering physics major, and I was the HMD developer.
So this is our team, and we use the Magic Leap 2 for our development. We've all heard the problem in all the mission descriptions, so I'm going to go ahead and focus on highlight what we focused on, which was LMCC development, LMCC connection to the HUD, and some additional control schemes that we wanted to do a little bit more research into. So this is the overview of Mike, our design. As you
Welcome
can see,
to Mike, the Mixed Reality Information Kit for Exploration.
There are two screens and our compass, and that's what shows up when you open up the application, the little head of Mike. And then here is our upside down chest-mounted unit, which we decided to create to mimic the DCU on the XEMU. And that controller is where the screens mount to, so they are torso controlled rather than head tracking.
So to go a little bit further onto the two screens in the HMD, so we have a dynamic screen and widget system. So on the left, you can see this is our left screen and our right screen. The left has 4 widgets: the vitals, input devices, LMCC, and settings. And on the right, we have the navigation, spectroscopy, and our task viewer. So this is our task viewer, and this is how we convey to the astronaut what they should be doing. So we have a list of all the different procedures that they might have to do while they're doing an EVA. When you click on one, you can see on the right in the task viewer the current procedure. It tells you whether or not what you're doing is on the UIA, the DCU, or on the HMD. And they can go throughout the different tasks. Next slide.
So this year for the LMCC, we decided to experiment with using extended reality on both the EVA side and also in mission control. So our entire LMCC was built in VR with the MetaQuest 3. Here is a little sped up video going over the system. As you can see, there's a bunch of different slots for screens. This is infinitely customizable. The user can put the screens wherever they like. As you can see, they're spawning them in. So if you don't want to have the information overload, you can also hide screens that you don't need. And then I'll go over a little bit about the specific screens themselves in the next few slides. A lot of the screens are similar or almost identical to the ones in the HUD. And then you might have seen down at the bottom there is a 3D map of the rock yard, and we'll talk a little bit more about that later. That ties to our waypoint system. So there's a still image of the full layout. There's just an example of one setup that you could have while using our LMCC. There's the VR hands, the central nav bar, the 8 different screens, and then there is the map. So here are 2 additional screens that the LMCC incorporates that aren't in the HUD. First one is the rover screen. It shows the rover's position and heading data, and then also has a live feed with that button there to swap between the thermal and normal views. And then off to the right, there is the important systems screen, which ties directly to the telemetry stream with the DCU. So if our design evaluator changes one of the switches, that will update on that screen.
So here's how we implemented spectroscopy, both on the HUD and the LMCC. So for the rest of the presentation, if you see anything with a white border, that is our HUD, and if you see anything with a green border, that's our LMCC. So upon scanning, you'll get a notification that there is a new entry in the spectroscopy screen. So it'll pop up in a list like this with a little timestamp, and when you click on it, it'll give you more information on the sample itself. And then on the right, that's how it's implemented in the LMCC, where you can see the different percentages and whether or not it's a good sample. So onto navigation on the left, this is how it's implemented in our heads-up display. So using the height map of the rock yard, we use the A-star pathfinding algorithm to create the best path to the desired waypoint. And we use a green line to bring you around the craters and the mountains. So we're in our hotel room here, but when you're actually at the rock yard, it'll navigate you around the craters and around the mountains. And on the right, you can see we have, in the LMCC, you can grab waypoints and you can drop them on different points in the map, and then they'll appear in the heads-up display for the head-mounted display.
So finally, we want to talk a little bit about the communication between the HUD and the LMCC. We implemented a semi-functional audio messaging system. As you can see from the screen over there and then the screen in the middle, the HUD and the LMCC can both send voice messages to each other, and then they will appear on either side with timestamps. And you can click on the voice message and you will hear the audio. We didn't use this feature too much during testing since we were provided with one, and it was better, admittedly. So we just stuck with the headset that they gave us. But then off to the very far right, that is the astronaut camera screen in the LMCC, which has a live feed from the Magic Leap 2, which is the heads-up display that we used. And that camera is pasted right there on the live feed.
So for this year's design challenge, we chose to focus on the control schemes aspect. Up here we have our glove that we were able to kind of design with finger controls to move around the screen itself. And then, as previously mentioned, the design, the chest-mounted unit, that was 3D printed to hold the controller, and that kind of just sits on your chest and you strap it around.
So here is, the first video is our glove. So you can see it right here. You can press the different buttons and it'll light up that specific finger. And then in the second video, once it plays, upon turning on the glove, it's completely wireless, you'll get a notification that a new input device has been connected, and it will appear in the input devices widget on the left screen. Once it appears, you can see all the information about that device. So it'll custom implement different controls. So the pointer finger and the middle finger are the interact keys, so you can click on it to click on different buttons. You can see the glove appeared there. And then the ring finger is, it's on the scout mode. So scout mode will turn off all of the screens. So in a second, they'll turn off all the screens just by using the ring finger.
And for future development of our control schemes, we wanted to also have on that chest-mounted unit a DCU, and that would be with other inputs in the future for like future development of control schemes, and kind of have like dials, like a joystick sort of movement to also control the screen, to also be able to implement that human factors testing and to see kind of what the user would feel that is easier for you to use on the screen itself.
Okay, so this is just a quick overview of our general systems architecture. As you can see, the head-mount display and the LMCC both communicate peer-to-peer over UDP, and then the input devices themselves also communicate over UDP with the HMD. So all devices do need to be on the same Wi-Fi network, and then both of them make requests to the telemetry stream. So here are two more experimental features that we incorporated fairly last minute. But this is to further show the immersion between the HMD and the LMCC. If that second video will play. So off to the left here, we actually fully hand-tracked, using the Magic Leap's hand tracking, we networked that data and send it to the LMCC. So there's a image or a screen or a video from the map on the LMCC with a little astronaut model that we got. And it shows the moving hands from the Magic Leap. And then over here, this is, the name that we're using right now is Celestial Oversight, but we're open to suggestions, of course. But as you saw there, if I can play it again. Never mind. But as you saw there, if you remember from the navigation video, the user's hands were over the map, and those hands are actually fully networked. So we sent those to the Magic Leap user, and they can see them in real time. Our design evaluator had a lot of fun with that one.
So for outreach, our university hosts a research symposium called Discovery Day. So we were able to present a bit of an outline of our design to all the faculty and students there. And our university also has astronomy open house nights, which is open to the public near the campus area. And we were able to also kind of just give that outreach to other people like across like our area. And yeah. Thank you all for listening, and we will now open it up to questions.
Very cool glove. It's always great to see you guys back. So I noticed you had a digital twin of the astronaut in the MFCC environment. What is the intention with that? Is it just purely awareness of what the crew member's doing? What are some problems that you could solve with that?
Yeah. So the astronaut being on the LMCC, it was mostly just, it was a neat feature that we thought we could implement to, I guess, show how VR could be used in the mission control side. It could also show maybe like a little bit about what the person in the heads-up display is actually doing, whether they're currently interacting with whatever they're doing, like if they're reaching down to do like spectroscopy data, or if they're currently interacting with the panel, or if they have their hands up for some reason. It just shows a little bit more data that the LMCC could grab and then potentially use to help assist them.
Sounds good. And then for your glove controls, is it purely mechanical controls? Is there any computer vision that's happening with the glove itself?
So it's purely mechanical. Originally, the idea behind the glove, it was Miranda's idea to make it where the different touch inputs on the finger, it was just a like pressure sensor or something that isn't as mechanical, like having to press a button. But we ran into some issues with noise trying to get those values consistent, so we wound up switching to buttons just to show the proof of concept. But there's currently no computer vision or anything else being used.
Thank you, and thank you for the creative solutions.
Really cool presentation. I really liked your guys' idea to use a VR headset for your LMCC instead of like a web design. One question I had about that is like when you were doing your test in the Rock Yard this week, how did you feel like your headset LMCC software, like is there anything you would change about it or anything you noticed that you didn't expect in design versus in implementation?
Yeah, definitely. So one feature that we actually planned to implement, unfortunately didn't get around to doing, is making the LMCC in full pass-through. The MetaQuest 3 has full pass-through technology, which basically just overlays the real world over the virtual one. We didn't get around to that, unfortunately, so as you saw, it was just the black background. But this would help the user in the LMCC still be connected to the people around them and not to sort of be like pigeonholed into directly helping the person down on the EVA. That was something that I ran into because I was the main LMCC user and I couldn't really figure out what was going on around me, and people would ask me questions and I wouldn't answer them because I was too zoned in. That's one thing, and then the other thing is using hand tracking. So we're still using the controls for the LMCC, but the goal at some point is to eventually incorporate full hand tracking where the user can just reach out and then pinch and move menus around. So those are two features that we would like to add.
Very cool. Thank you for your ideas.
Thank you, Team Mike. Next up, we would like to welcome Team Chuck of Boise State University.
Hi, my name is Ainsley Iverson. I'm team lead of Team Chuck. We're a team comprised of seven students, 6 undergrads and 1 graduate student, and we are from Boise State University, and we are here today to talk to you about Chuck's holographic user control kit. So our goal for this challenge was to use our system to increase the autonomy and efficiency of a Martian EVA. We were able to do this through our 5 primary subsystems, partially due to the large variety of majors on our team, including computer science, mechanical engineering, electrical engineering, and games, interactive media, and mobile gaming. Next slide, please.
Okay, so this is a brief overview of our systems. From NASA, we are getting all of the information from the rover vision kit, basically the whole state of the simulation, through their telemetry server. On our side, all of that goes into our master control program, which is definitely not a Tron reference, which then basically stores and synchronizes that data between our head-mounted display, which is our HMD, our LMCC, and any peripherals that we have for that. So for the LMTC, we decided to create a website that would display information, whether it be biometrics, procedures, our map, and let the IVA place pins and update procedures and basically view the state of the mission.
So I was a lead designer on our HMD. My goal was kind of to create an extraterrestrial Iron Man suit. But I really wanted to also focus on creating a lot of autonomy for our EVAs, reduce their cognitive load, and really improve upon their situational awareness. And so some ways that we did that was we created a biometrics that when they hold it up, we'd use colors to help signal emergencies. So things that were good were green, things that popped red drew their attention and notified them that something was wrong here. We also had what we called a timeline. And this timeline allowed the EVA to completely manage their own procedures, track their time on these missions, so they can kind of manage to see where they were without having to always talk to the LMCC. So while the LMCC could communicate with HMD, they could be completely autonomous in case there was communication errors. We also had things like navigation that they could look at, and they had all the access to the LMCC data if they wanted to look at it. But the main ones were definitely the summary timeline.
The armbar was created to be used as a 6-key peripheral to be connected to the HMD via Bluetooth, and Kendall will be explaining the purposes.
So we decided to do armbar after doing some thought and research about what an astronaut would be capable to do in a pressurized suit, and we found that operating menus inside of AR with depth perception and field of view, and trying to operate those menus was a little bit difficult and complicated, so we decided to go with the armbar as our primary function to operate the menus. We also had a voice activation as our secondary. We decided not to go with the voice activation of the menus because of heavy accents, and voice inflections could cause problems with that, and it depends on also the stress of the astronaut could change voice parameters. So we decided a simple keyboard for that. We also just decided not to use a hand device As a pressurized suit, any sort of hand movements and stuff would create hand fatigue, and we wanted to avoid that in their EVA, or if they're holding a rock or some sort of device or tool, we wanted to not have our armbar or a device get in the way of that capability.
Okay, so from our first day of testing, we had some takeaways. We really liked our performance of how our system worked. It mostly worked great. We hit a few things for improvement that we worked on for our second day, but it mostly went well.
Hi, my name is Digno JR. We had a really fun time here at Johnson Space Center. Testing in the rock yard and the analog was really fun, and we received a lot of good data about how to improve from test day 1 on test day 2, especially in regards with the design evaluator. They gave us good feedback on the look and feel of using the windows. And so we found that as a result of the EVA having access to procedures through the summary timeline, Chuck enabled them to have increased situational awareness as well as autonomy, as we've experienced the fun of having connectivity issues on site. And so practicing that autonomy in situ was really beneficial. Specifically, we also improved windows stacking on top of each other, as when you activate the armbar, they keep looking at the same spot, so your windows would pop up in the same spot. So we fixed that for test day 2, and as a result of that, the design evaluator regularly utilized Chuck's customizable window operations, such as following the views or their persistent location, depending on their situation.
We found our design evaluator really enjoyed using the armbar on day 1, and so we wanted to optimize and utilize our armbar more for testing 2. So we implemented an eye tracking device so they can look at whatever menu they want, and they can open and close it or have a next or back capability for that.
Another feedback that we received from our design evaluator was that the extra laser cut hollow tint attachment that we created was helpful in being able to see the displays.
Next slide, please.
Okay, so some of our fixes from our first test day, we fixed some of our networking issues that we experienced with our LMCC. We were able to greatly reduce the lag and at least communication between the LMCC and MCP.
And as a result, we found ways to improve on window manipulations, as well as we found success with our minimal design aesthetic in enabling cognitive workload, or improving it.
And so seeing as we had very little time to be able to test with different users the armbar prior to our design evaluation, our goal in the future is to be able to have new users interact with it and be able to improve its intuitiveness, its design, and functionality. And so in the future, we would like to explore different methods of interaction, such as tactile affordances.
One of the things that we wanted to really improve upon with the HMD in future development was making the menus easy to learn, easy to navigate, and very intuitive. We wanted to do this through improving the color scheme, kind of look at some of the resources that NASA might have for the types of colors we should be using for certain notifications, improving icons so that way people are assuming that the icon is directly related to something, so kind of add more icons to the screen so people are just keyed into what they're looking at and are expecting to look at a specific menu. We also want to kind of improve upon the things that we can add to the HMD and the customizable ability of it to suit the astronauts' needs as they're out in the field.
And for the LMCC, sort of along a similar note, we're planning on extending the customization that's possible to allow the IVA to more easily see and access the information they need.
So our system is named in honor of our technical lead and very close friend, Chuck Burnell, who passed away about 1 month ago. Chuck has been a part of Suits since the very first Suits test week. You can see that picture in the middle was taken, I think, 7 years ago now, and he's been a part of it off and on. He was instrumental to our project and is a very large part of why we're here today. He was a very close friend of all of ours, a Trekkie, an engineer, and in his own words, the stray cat of our engineering department at our school, because he was always going from person to person, helping them out with each individual project, no matter he was busy pursuing his master's. And so we would like to continue his legacy in the aspect of always being available and willing to help others, no matter how busy we are ourselves. And we'd just like to say to, can't do it with that hand, to live long and prosper, Chuck.
Awesome dedication to Chuck. So we have minimal time. I have a question for you with regard to the arm bar. I really love the innovation this year on that. And I wanted to talk to you a little bit about redundancy. So if we have, if I'm an astronaut on Mars and my arm bar and my buttons don't work, what do I do?
Yes, that's a very good question. This actually also extends to Digno. So not only do we have the ability to access all the menus and displays, thank you, just through the arm bar, but we are also able to be able to navigate all the menus and displays through the HMD. And so that's our form of redundancy.
This includes hand tracking by manipulating the buttons. This includes voice controls by looking at the buttons and saying the words. And I believe LMCC also has ways to programmatically update the views of the HMD from the...
Thank you.
You mentioned that you received feedback on your armbar to have a back function. Was that during your evaluation in the Rockyard? And what was that feedback specifically? And was there another function that was requested?
Yeah, so initially on day one, we had a minimal viable product of the armbar just opening and closing windows, but the design evaluator asked us if we could implement the ability to traverse through procedure steps using the armbar as well. And so on design day 2, we implemented that, and we found success in them being actually able to navigate towards or forward or backwards through that procedure.
Okay, that's great that you were able to implement it live time. Great job. That's great.
Thank you guys so much. And I think I can speak on behalf of all of us that we are so sorry for your loss, and you guys are doing an amazing job carrying on Chuck's legacy. Next up, we would like to invite the University of Texas up. Come on up, guys.
Good evening. We're really excited to be here. We had a really lot of fun. We are Team Cosmic. We are a group of 5 aerospace engineering majors. We all graduated and we participated in this competition for our senior design challenge. And so this is Ty Nelson. I'm Dale Daniel. Probably should introduce myself first. This is Jordan Thomas Acampado. This is Luis Chavez, and this is Matthew Underhill. And so we worked really hard, and we're really excited to show you guys what we did. So what we set out to do, so we wanted to make something that was dynamic and was presenting multiple solutions throughout the entirety of the EVA. So we didn't want to get stuck, or really we wanted to focus on the cognition of the astronaut. On every single step, we wanted to focus on how are they operating, how are they feeling, what are they seeing, everything to do with that. And so we took the NASA Task Load Index and we pretty much tried to integrate that in every single step of our design. And so our entire design is focused on limiting cognitive load and analyzing it. And so we wanted to focus on augmented cognition. And so that is defining cognition. And so we wanted to take procedures to evaluate it using pupillometry and various other physical parameters such as metabolic rate and stuff like that. It's our first year in the challenge, and so we weren't totally sure about the spoofing of data on the suit, and so we were assuming we'd have heart rate and stuff like that. And so not having that, we tried to pivot, but we really focused on augmented cognition in our design. So this is kind of our LMCC. We did a lot in the Quest as we didn't have experience with HoloLens moving into the challenge. And so we coded our LMCC first in Quest, and then when we got the HoloLens in March, we began transferring it over, which mostly went pretty smooth, but there were some things that we had to work on. And so we built our TSS. We wanted to build our own TSS server between the LMCC and the HMD. That way we could send information over WebSockets. Our idea being we wanted everything to happen in Unity on the LMCC, being our software is doing the work, the LMCC is doing the work, but the astronaut is not doing the work. We wanted to take everything off of their hands, and we'll talk about how that worked and everything. So our design was very internet-oriented. Everything was happening on the LMCC, and we're pushing it to the HoloLens. And so on testing, when connection didn't really work out, we had to do a big... And so this is some of the stuff that we looked at going into our design, talking about dilation rate. So how dilated are your pupils based on brightness? How are your pupils moving? Are they moving quickly away from the center constantly? Are they focused on where they should be looking? Are they not? So that's stuff that we were really looking into. So HMD cognition, this is really where we focused the most of our project and what we were displaying to them. And so we had this circumplex model of effect down here in the bottom left, which is our circular. We wanted to produce a circular confidence interval based on pupillometry data, where we are mapping a point on this based on the dilation and the movement of the pupil. And so this turned out to be extremely difficult because as a team of 5, we're only testing it on ourselves in the HoloLens and the data. And so we're trying to build software that is taking a baseline of your pupillometry data and the brightness of the room and trying to account for all that and define where you are. And so we really tried to focus on how are different colors affecting you, opacity, background, brightness. And so we really focused and did a lot of research into greens, reds, what colors can be next to each other, what can't, what can we display on the HMD, and what, like, should power be a slider or should be a value that is indicated. What should be opaque, what should be see-through, stuff like that. And so we really focused on that. And then we really looked into some DARPA studies. They did Defense Advanced Research Project Agency. They've done a lot of stuff with fighter jets where fixing a body and analyzing how a person's body changes over the course of doing cognitively task, like very mentally draining task and how that would affect. So we specifically talked about or took note of a study about how fighter jet pilots are how a air traffic controller, how their cognition severely deteriorates after being responsible for maintaining and like controlling 2 things, and how essentially you can only really focus on one thing at a time. And so that's something we really wanted to focus on in our HMD and just how we implemented everything. And so you can see we have one objective, previous objective, and next objective. So we didn't want to show everything at once, but we wanted to show kind of where you are at relative in your procedures. And then if you indicate confusion, you're taking too long, we're going to show you on our HMD more instructions. We're showing you scan data. Something that didn't turn out to be super relevant is we wanted to indicate where if there was an error or like a suit leak, something that where we would indicate that. And so that's something that we kind of looked into that wasn't super relevant. Oh, hit the wrong button. Sorry. So test day difficulties and takeaways, like I said, we built pretty much everything on an online connection. And so when the TSS went offline or the HoloLens turned off because it was too hot, basically our design kind of went down the drain. And what we ended up with is an HMD that gets stuck. And so what we kind of noticed was we need redundancy in a way for the astronaut to really take it, or the design evaluator to take the situation into their own hands. And if the mission goes completely offline, they need to be able to complete the mission and return safe. And so that's something we really started to notice is we didn't have enough redundancy in the system where you make a mistake in the procedures or you skip a step. Do you have a way to figure out that, or do you have a way to undo that? And so we really started realizing that we had not taken into account that. And so we had built a design that was primarily focused on working in being great when everything's going great. And we really pivoted after the first test day. And so something we did is we kind of rewrote our LMCC using an API to have more flexibility. We didn't have a ton of experience coding in Unity, and so when we had a problem to fix it in Unity and then pass it across WebSockets, turned out to be extremely difficult when we're just get a video feed or something like that. And so we really focused on having a way to do live changes on the LMCC. If something's going wrong, maybe you do need to write code in that moment to fix it. And so taking that into account. Also, what would an astronaut want? So we're assuming that these people are highly intelligent, and so we wanted to take into account of if everything goes wrong, for instance, the HoloLens turns off and all of your positional data, all your pins are suddenly shifted 30 meters to the left, the astronaut, being an intelligent individual, should be able to take a relative position and the last transmitted position as a true value and then orient the map. So that's something we were really focusing on at the end, is having navigation when you don't know your position. And so only having north and the astronaut taking their relative position, they can indicate on the map where they are and then adjust based on that. And so the real big thing for us was the umbrella. We needed that on day one. So future work, talking about kind of what worked, what didn't. So we really do want to focus on augmented cognition and observing how someone is observing the task load index in a real quantitative value, not just time, but everything from pupillometry data to heart rate, baseline, and algorithm. So that's how the light is coming in off the HoloLens. And so that's what I'm talking about when I'm talking about background contrast variation. We used the tint as recommended because we initially were going to do a color gradient on the screen to shift for brightness and like have more optimized colors on the screen. And NASA kind of recommended that would be really good, but we initially had thought the ingress was going to start outside, and so the lighting shift was too strong, and so we had to kind of scrap that feature. But all being outside, it probably would have worked. And so looking forward, we're talking about really like taking the outside environment and looking at our design evaluator and building something where we're looking kind of both ways, not only out, but looking at our design evaluator and seeing how are they doing and seeing if there's something we can do about that. And a limiting factor, that's just something that the other teams really talked about. We had as the other teams did, had systems to indicate an off-nominal value, but maybe a value that has a rate of change that is too high. Your oxygen's not necessarily low, but it's dropping. Maybe there's a leak or something like that. And so that's stuff that we wanted to look into in the future, is how can we observe rate of change, stuff like that, moving forward. Yeah, that's our presentation. Thank you, guys.
So I had a chance to spend a little bit of time with y'all at Poster's presentation. I really like the fact that you're using an anticipatory design with AI. So I'm curious to know future, right, in terms of further validation as well as implementation of that gives astronauts an ability to kind of predict things in a way that gives them the opportunity to respond even before there's a challenge or a problem.
Yeah, so I think you're talking about how, are you talking, like, I'm not sure I'm particularly understanding your question.
So
actually.
what are you doing next in terms of the implementation of the AI?
Okay, so we want to build a set of algorithms based on heart rate. And so in having the HoloLens for only 2 months and not being super experienced with it, tracking and taking internal data from the HoloLens turned out to be more difficult than we were anticipating. And so we really want to build algorithms, whether that's just weighted values of vector math, but implement a method of implementing everything together. So not just having pupillometry where, okay, we're trying to do a confidence interval with pupillometry, but we also have this metabolic rate of integrating all of our systems together. And so we can truly have, like, the idea is you have a perfectly point on your confidence interval of a super tight confidence interval if this person's having fun or this person is very bored. And so I think integrating all of our systems, integrating everything together would probably be the next step forward. And also, I think something that would really help with that is suits aren't necessarily a spacesuit isn't necessarily on the face, and so there's distance between the screen and the face, and so your face will change based like micro gestures and gestures on your face, and so looking at how the astronaut would change their facial features is also something we're really looking forward into, like how could we view confusion on your face, stuff like that.
Can you give an example of how you changed a UI element based off of pupillary data?
So I think one thing that we did was putting things on the end of the screen doesn't, like, all things all the way at the edge of the screen doesn't really work, and so people don't see them. And so trying to take, basically an important notification needs to be in the middle. I'll mention the other one team where they did the testing and people aren't seeing an alert. And so kind of taking that and seeing, are they even, how far are the pupils going to, like, if it's opaque, if it's not opaque, how far do the pupils change from the center? Or how fast do they change from the center based on stuff like that? I think I answered your question.
Yes, thank you. So like location of items on the screen versus where their gaze is. Thank you.
I could also answer a little bit more about that. With the eye tracking data, we wanted to measure eye tracking movements, so basically the velocity of your eyes at a time and also the dilation. And depending on the speed, if it's off nominal, we would change the UI dynamically. And so say your eyes are moving, darting around, and doing all of that, we wanted to limit that usually indicates that you're confused, and we wanted to limit the UI so you can hone in on one specific element and basically make it easier so you can focus. And so that's another aspect. But coming to Houston and like having a high stress environment, eyes were darting around everywhere, not really nice to implement that, but that's just one example.
It's a very creative solution, so thanks for bringing that.
Really great presentation. I like that you guys looked into like colors of the different UI elements because like I have some friends who are colorblind, so like those colors are really important, especially if someone has those like limitations. One question I had was it seems like you guys had a lot of like challenges during test day. I was wondering if you would, knowing this now, what sort of testing like changes or what things you might have tested before your design test day you might have done?
Yeah, so I think one thing that we didn't take into account was we always tested everything as like, okay, this functionality works, we're connected to the internet, everything's working, and I think we never anticipated that something wouldn't work. Like, truly anticipated that, okay, well, the TSS is transmitting nothing, or we're scanning and this isn't working. And so I think truly accounting for what is the problem that we're solving and like what really is the mission is like truly trying to take into account that, I guess.
I think we also underappreciate the value of really good network connection because in our code and everywhere else, like usually on our phones we can stream YouTube videos at 180 quality and 60 frames per second, but we didn't anticipate not having a really good internet connection, so trying to do that was not good. So a design change that we've made was basically changing our video qualities, everything like that, like 144p, 1 frame per second at one point, but that's just how it goes.
Hey, just to let you guys know, I was in Arizona this past week doing field testing with the astronauts and crew. And believe it or not, that's one of the prime problems is comm. And we know that's going to be a problem on the surface of the moon early in the missions. We have no infrastructure. So literally they have protocols where they can keep on doing geologic surveys and picking up samples and things when they're out of comm with the MCC. So it's you guys are experiencing just what we're experiencing today. So it's exactly what we need. So.
Thank you.
Thank you, Team Cosmic. They also played salsa music during their test, which was a great morale boost at the end of the day, so thank you for that. Last but very much not least, we would like to welcome Team Cosmoshocks from Wichita State University.
Now, I want you to make yourselves comfortable and settle back. Now, are you all ready? Here we go.
Hola.
Buenas tardes. I'm Yumi Kikuchi. I'm the co-lead for the Cosmoshocks team. Our team is composed by a mix of graduate and undergraduate students. We have 6 different majors, and we have 2 co-leads, 2 graphic designers, 1 geologist, and 4 developers. Basically, from the beginning of the challenge, we wanted to focus a lot on the user-centric approach, and that took us to have decided to have an HMD with a simple design and an LMCC that could communicate efficiently all the needs of the mission. Now we're going to focus on the design. Basically, this is the last version of our design after feedback from design review and human-in-the-loop testing. We spent a lot of time figuring out good contrast and color decisions for the HMD, and also we spent a lot of time defining how we were going to, can you go back please? How we were going to display the telemetry data, the EV information basically, and that was very good feedback from our mentor Amanda, who proposed that we could display it in a table for easy readability. Next, we had the LMCC. We had 2 screens on the left side. We have the main screen where we have things that are static and that are on display all the time. Focusing on the biometrics and the camera feed, and then we had communication tools and navigation tools. On the other hand, on the right side, we had different tabs where you can manage different data with more detail, with a focus on the procedure management where you will have more access to see time of each task, time of each procedure, and each step that you had to follow.
So hello, my name is Danae Sawyer, other co-lead for the team, and we used Unreal Engine as our code for our LMCC and HMD, mainly for the focus of wanting to stick with an industry standard, working in an industry standard, and also for our team that didn't have computer science majors or any backgrounds of that variety. We were able to work in a more quickly, or we were able to develop more quickly, which aligned well with our constant iterations for our agile methodologies that we use to manage our product. So as Yumi already said, we wanted to keep a simple design for our heads-up display. So what this resulted in was keeping the very bare minimum on the display, so that way, again, to maximize field of view and to reduce that cognitive load. So we were only streaming the necessary telemetry data that was needed. We only were using the voice command mainly with LMCC and HUD, with looking forward to redundancy, other forms of redundancy for safety reasons, and then using this to aid navigation and procedures. With all of the needs for compensating for a bright environment on Mars, we had, as other teams have said, worked to tint when to address the glare, as well as a blinder print as our other peripheral device. However, with redevelopment issues, we went through not 1, not 2, but 4 different versions of the peripheral device, but that did stop the glare. With the LMCC, since this is the piece of the prototype that is needing that full autonomy, this is where we're addressing a full management of procedures to aid EV and IV procedures in navigation and tasks and missions, as well as making sure that we are prioritizing a full access to detailed telemetry data so that the astronaut, or the IV, pardon, is able to have that autonomy. So with our outreach, just as NASA provides a variety of career opportunities and industries within the organization, we wanted to ensure that our outreach had the same effect, that we were addressing and reaching out to upwards of 500 participants, including high school females, where we were speaking with them, sharing them the career opportunities of NASA so we can level that knowledge so they can have those same access to opportunities, as well as our other forms of outreach of monthly blog posts, monthly blog updates, social media presence, and events across campus and other schools and high schools. We also were able to win a People's Choice Award at our Graduate Research Symposium.
What up? My name is Nathan Lewis. I'm developer for the Cosmo Shocks team, and I'm going to go over pretty much what we learned at Test Week and how we kind of changed things around. For the results we got from our first test, communication in the actual setting was very different than what we experienced in a lot of our prototypes. So particularly with voice commands being involved, like it changed a lot of our perspectives, so that was an important pivot. Also, we had received some really good feedback about stationary user interface elements. We were so focused on having everything attached to the view, and obviously there's a lot of obstruction that can occur while you're trying to fix a comm tower. So we received some great feedback to have some things that were more stationary that you could put off to the side while you work on things. Also the integration of varying systems. Obviously we were very focused on LMCC, HMD, but then when we come out, we're integrating a bunch of other things, XRF scanners, all these other elements come into play, so getting those to integrate. Also, I just have to point out, if you can go back, just that photo is also just the perfect representation of us thinking on the fly, trying to solve solutions there on that first test day. So in terms of lessons learned, again, integration was a big thing. So like for us, it was really important for us to take in the whole picture. In terms of all of the elements that were not things we could simulate back in Wichita, Kansas. Obviously, the rock yard is a big one. We had a really unique experience too, testing in like super bright, crazy conditions Monday, and then really cloudy conditions Wednesday. We were peeling tint off in the morning, in a panic for how much tint we had put on. Also, we learned lessons about what we needed to prioritize. For example, we were kind of like down to the wire with getting our video feed, and we were like, well, there's voice comms, we have other things, it's not going to be that important. We learned Monday video feed is probably the most important thing. So that was like a big thing, was understanding where our priorities were. And also validation, that everything we do should bring some level of value. Again, we just had certain elements that we were really highlighting that on a theoretical level we thought would be really important. We wanted to have as major points in our user interface design. And we realized that those were actually obstructing important details like suit pressure when we were doing egress. In terms of future steps, also, man, the photo's so good, I guess we used it twice. In terms of future steps, obviously the autonomy of the local mission control center was a big one. I think we had a group touch on that in terms of having the actual device running your LMCC, also being the thing that provides all of your other data. When we're looking at this being something that's actually on the surface of Mars, we saw that as a really cool opportunity moving forward to try and improve the autonomy of the LMCC. Also, again, redesigning the interface we saw as a future opportunity. With the amount of graphic design we had on our team, we had a lot of really incredible perspectives about making designs that were very appealing and very functional. And yeah, we've learned so much in this semester. We think that moving forward, we have the opportunity to improve even more. And thank you so much for having us out. We really want to thank, the Suits team, Adam, Geraldo, all those Zoom meetings that you guys helped us out. We genuinely couldn't have done it without you. So thanks for having us out, and we hope to see you guys in Houston again. Thanks.
Hi guys, thanks for a great presentation. I was able to go and test your project out on Wednesday as a design evaluator, so it's really cool to see your project and then also hear your presentation. I wanted to ask for what you mentioned on the, I think, second to last slide about the elements that you feel, which elements do you feel you would focus on more in your HMD and LMCC?
As far as design-wise, I'm a graphic designer for the team. Elements that I really focused on, that we really focused on, was procedures and making it more simplistic as far as the biometrics as well. Putting them on the right side, biometrics on the right side, and procedures on the left side. And yeah.
And then I guess for like a development side, we got some good insight that we should maybe not have the designs visible all the time. Maybe just use a voice command to bring up your telemetry stream server information. So like your oxygen levels, you don't always want to see that. It might just stress you out. So if you're if you're needing to know that while you're doing your procedures, you just pop it up. Or also in addition, like doing your procedures, maybe you just pop up that procedure and then you just can go back and forth, but it's just a little side window, not stuck to your viewport as we originally thought we needed to do.
Thank you. I noticed you have a geologist on the team. How did that impact your design and how you approached your UI?
Yeah, so actually really early on when we formed our team back in fall, we had a meeting where everybody brought kind of information about their specialty to the table. And one of the things Elaine brought really quickly was the importance of knowing where a sample was picked up. And that was something that hadn't really occurred to us in terms of it. Again, we're just feeding spectroscopy data. It was just like streaming it from the server was our priority. And that was like, perspectives like that were hugely important to us understanding what data was going to be relevant and what data hopefully future iterations will include so it's more relevant to the mission.
One, you mentioned, and it's a great idea because we got to get there. For Mars, we're not going to be able to be over the shoulder with the crew watching you. There's going to be a time delay there. And you mentioned about the autonomy. Have you started thinking down the path of AI and how that can help your autonomy?
We haven't really thought, we haven't we've kind of considered it a little bit, but we haven't actually gone down that direction. But I can definitely see kind of where that would play a very large role in the autonomy of that sort of thing.
Yeah, the joke we say here at JSC is when we have people in mission control, you can see 15, 20 people on console. And it says the idea with Mars is we have to take that and put it on board the vehicle. How do we do that? Because we can't put 20 people on board the vehicle, right? So that's why I think AI is going to play a big role in that, helping out with the crew.
Thank you, Wichita State. So that will conclude our student presentations, but not our live stream or our presentation. I want to invite up the NASA Suits Activity Manager, Jamie Semple, to talk to you guys a bit about some cool awards that we have today.
So NASA Suits is one of 8 Artemis Student Challenges. And this year, the Artemis Student Challenge team established 3 awards to recognize outstanding performance by a team or individual. The first award is the Pay It Forward Award, which recognizes outstanding community. And Speaking of technical problems, I think we're good to go. Yeah. Okay. So audio is back. And then the third award is the Artemis Educator Award for a faculty member who went above and beyond to help their team achieve more than they thought possible. So each awardee will receive a certificate that has a flag, an Artemis flag on it. This flag is a piece of spaceflight history and was flown on the Artemis 1 mission in 2022. I'm going to ask our SMU panel to help us. Each individual panelist will come up and award one of the awards that we will recognize today. So we're going to start with the Pay It Forward Award, and Tim, if you want to join us. Pay It Forward is presented to teams for impactful education engagement in their community or beyond. Today we will recognize 2 teams. The first team went above and beyond with a diverse range of educational outreach events. They span multiple age groups and interests, sparking a passion for STEM and beyond within their community. Their dedication is truly inspiring. Please join me in welcoming Team Chuck from Boise State University. Come on up. Okay, I think we're good. Thank you. All right. Katie, if you'll join us. Thank you, Tim. So our next team consistently stood out for their unwavering support of the Suits community. In a challenge where ambition thrives, this team consistently offered helping hands to other teams, fostering collaboration and shared success. This commitment to the greater good is what truly sets them apart. Congratulations to Team Jarvis from Purdue University. All right, Dr. Cherry. So the Artemis Educator Award is given to educators, faculty, or mentors as nominated by student team members who were inspired, motivated, and achieved more than the team members thought possible. This award acknowledges the time, dedication, and commitment to being an exceptional educator. This year's recipient exemplifies what it means to be a phenomenal educator. They prioritize creating a respectful and trusting environment while fostering open communication even on difficult topics. This year's award winner truly made a difference, with the students saying their guidance has been instrumental in the team's success. Their encouragement of iterative design helped them rapidly improve and identify issues early. They instilled a culture of professionalism, helping them develop and maintain a strong team. Please join me in acknowledging and recognizing our first NASA Suits Artemis Education Award winner, Kristen Waits from Wichita State University. So the Artemis Innovation Award for teams who showcased innovative ideas and solutions within the scope of their challenge for both technical and non-technical areas. We're going to ask that our NASA Suits technical advisor, Geraldo Cisneros, join us to tell you a little bit about this team.
Yeah, so first I want to say thank you to all the teams this year. Your tenacity, your resolve, sorry my voice is a little hoarse right now. Your attitude throughout the entire week has been phenomenal. We couldn't have asked for a better group. There are brilliant people in this room. And we're so excited that you all were able to impressed and excited with what you delivered this week and all the hard work that you put in. I know it's kind of a roller coaster this week with Monday, kind of the issues that we were having, but that's I think Sunday I had mentioned things will go wrong, and we want to see how you bounce back and what you do. So you saw that from our side, and like I said, everybody had a great attitude, and you showed great resolve, and I really appreciate that. So first, I want to give everyone a round of applause, and thank you so much. For this year's Innovation Award, I guess the first Innovation Award, every one of you had awesome designs. You had, like I said, we were super impressed. This Innovation Award goes out to the team who showed outstanding innovativeness, ingenuity, creativity. So I'd like to award this to Team Mike from Embry-Riddle University for their. Yep.
All right, congratulations to all the award recipients. Geraldo, don't go too far away. Before we wrap things up today, we do have some exciting news about 2025 and what's going to happen next year with the NASA Suits Challenge. So I'll turn it back over to Geraldo to tell you more.
Yeah, so we are working the new NASA Suits Challenge. So what we kind of preach when we're creating the challenge is to be descriptive but not prescriptive. So I know there's times when we're building it, we're engineers on the tech team, and we like to, when we're coming up with the design, we'd like to say, oh, it'd be cool if they did this or they had to do this, but so we're trying to not do that. So that's why we try to keep it somewhat vague so that we see what you can develop and what ideas you all can bring forward. So for next year's challenge, we are going back to the moon, and that's not just to beat the heat, but we want to see since that's kind of our next step is the moon. Mars is kind of the moon is our proving ground for Mars. So we want to see what you all can develop. We don't have any kind of concrete details just yet, but we will look at things like automation, crew safety, a lot of the things you see here, but it will be expanding some more. So we look forward to all of your proposals. We look forward to seeing you all back here. And again, thank you all so much for making this week amazing, and I hope you all enjoyed your week. Thanks, everyone.
All right, guys, we made it. That is going to wrap up our exit pitches. Can we give a big round of applause to somebody that's viewing you guys online? We have Adam Peterson that's viewing you guys online. Please give him a big round of applause. Yes. As you guys know, he's put his heart and soul into this program and making this enjoyable for you guys. So he gives his best, and I know we all give our best to him. One more round of applause for you guys, our tech team, our expert panel. You guys did it. Great job. And that will conclude our live virtual presentation today. If our students could hang back for some team photos, and then we'll let you guys go. Thank you guys so much.